why don't you work with Vishak? I think he has a problem setting. Everything is there. It's just a matter of adopting your loss functions and also improvising on your loss functions. We can't be doing only that, right?
Okay. Okay. Yes, sir.
Okay.
Yes, sir.
And the next team will start. Who's the
Thank you,
next
sir.
team? Thanks.
Okay. Thank you, sir.
Be in touch with Vishaka, and you should work towards a paper submission. Yeah.
Yes, sir. Yes. Vishak, can you like share your contact or something? WhatsApp number, if that's okay.
Yeah,
Yeah,
sure.
yeah. Please do that. Vishak can do that on the chat.
Yeah.
Thanks.
Yeah.
Who's the next?
Okay. Okay. Got it. Thank you.
Yeah.
Thank you, sir.
Thanks.
Yeah.
Thank you very much.
After Dange. Vibration.
Oh, is the same person whom we had rescheduled, huh?
No,
Reschedule
no.
join. So we have around 8 teams left, isn't it?
Yes.
And we are done with 12. How many teams so far?
12, I guess. 11.
Sorry?
11 or 12.
Today? No. Total.
Total. Total would be 14. I guess.
14. I'm making a mistake somewhere. Okay, let them come. I think I'm making a mistake somewhere. Yeah. Can you just start the presentation? We are running out of time.
Yes, sir.
Late.
Slides are visible?
Yes.
Yeah.
Okay. Today we'll present our project preference learning inside generative tasks. And this will be the outline. We'll present language model.
Can you go back? Can you go back? Can you go back?
Yes.
So this is related to your
Seminar, yes.
seminar. Okay, go ahead.
Shall I start?
Yeah, go ahead.
I think RLHF and DPO part they can skip, right?
I'll just present very shortly.
Yeah, sure.
So language models primarily focus on modeling sequential data. So when we look at two variants of language modeling from the past and the current paradigm, we see that RNN-based language models process input in sequential nature, and they're able to capture the temporal dependencies as a process one input token at one time step. And when it comes to transform-based models, they instead rely on this all-to-all attention mechanism that capture significance of one input token on other tokens relatively and irrespective of the positions that they appear in the input sequence. Irrespective of that, both of these architectures primarily estimate the generation of the next token in a probabilistic manner, where given an input sequence X, they generate the probability of the current token based on the previously seen tokens. Now, when it comes to preference learning basically has originated from the idea of learning to rank. So given a set of instances and the corresponding set of labels, the goal of a classifier, that is preference learned, is to generate a ranking among the labels for a particular instance. And such a classifier is usually trained with some seed preference information. And basically these the loss functions that are used for these kind of ranking are basically the margin loss, where you prefer your preferred output over the dispreferred output while. Now, when it comes to language modeling, especially for large language models trained on vast amounts of web data, preference learning is generally implemented to put guardrails on safety measures on the safe usage of these large language models. And there are existing methods that fine-tune the unsupervised LM once it's been pre-trained to align with human labeled preferences. And in this case, mostly the preference data set that is used to train the model is basically consists of a prompt and human labeled choices over two model outputs. So these are basically binary decisions that they have to make between two model outputs. And one of the most used paradigm is the RLHF, where you have two models which work in turns together, the reward model and your language model. So I'll go through quickly. The two stages of RLHF basically involve the SFT stage, where you first train your model in supervised manner on high quality data for downstream tasks. And the second phase, you learn a reward model after generating two outputs from this SFT trained model. And the pair of these two pairs of answers are generally labeled by human annotators, denoting some preference of YW greater preferred more than YL. And in this reward modeling phase, basically it is modeled as a sigmoid of the difference between the preferred output Rx of y1 and the dispreferred output R of x y2. And then you learn a reward model using the maximum likelihood estimate loss, where you see we get the estimated the expected value as a log sigmoid over R5x of yw minus R5x comma yl. And then after once this reward model is learned, then you use this with the RL fine tuning phase, where you want to given output generated by the model. You want to maximize this reward for this particular instance and the model generated output. And you also want to restrict the model to go far away from the reference model. So that is why you also add a penalty via the KL divergence. And with the discrete nature of language generation, this object is not differentiable, and hence this requires reinforcement learning to optimize. And this is what DPO works on, and removes the separate stage of learning a reward model and going through the RLHF phase. So DPO, what it does is that it once we obtain the optimal solution to the KL constrained reward maximization step in terms of a generic reward model by R y given x and also the reference model. So once we use this optimal form of the reward function into our original reward model objective that we define in terms of sigmoid function of the difference between the preferred output and the dispreferred output, we get a closed form solution here only in terms of the human preference probability, in terms of the optimal policy pi star and the reference policy pi reference. So here the main benefit comes here is that the reward is now implicitly defined by the language model itself, and we do not have to separately train a reward model and go through the RLHF stage. Now, since our task is for set generative set learning tasks, so we cannot work with sequential language modeling tasks where the model expects input to be in form of input sequence to be textual and output sequence also textual and not sets. So we also explore the literature for set generative models. We mainly come across two models. One is the set transform model, which defines that any model that handles sets as inputs must satisfy two conditions. The first condition that the output of the model should not be input order sensitive. That is, it must be permutation equivariant. That is, if you apply some function over the inputs x, then the output given by the model should also be equal to function multiplied. So pi of f of x. So f of pi of x should be equal to pi of f of x. And second important thing for this set generative model is to follow that the idea that these models should be able to handle variable sized inputs. And this is where you can't use your vanilla feed forward networks because they will not be able to handle both of these conditions. And the second paper we come across was sequence to set generative models. And this paper suggests approaches to transform a maximum likelihood based general next token prediction language model to a set generative model, so that the resultant model now can assign probability scores to a given set rather than input sequences, rather than input sequence of tokens. And one of the approaches mentioned in this paper is GRU to set. And this utilizes the GRU architecture, a basic variant of the RNN architecture, which is where we can represent this architecture as a Markov decision process by a sequence of states and actions. So you might have states S1, S1, S0, S1 up to ST for T time steps. And once you are at every state, you can let the model perform one action. So when you compare to basic language modeling, the states will be the time steps where you process the input, and the action is the generation of the hidden state at that particular state. Or if you are looking at a decoder based model, then at particular state you output a token. And then for modeling this sequential GRU as a set generative model, each of the state in the state space is used to represent a set of elements, and every action that you're doing in being at a particular stage at a particular state is to add an element to the set. So this sequence model can be transformed to output probability of a set in the following way. So so L basically is the path taken in the state space to generate some set S. So you might have different paths taken in the state space to generate the same set S. So the probability of generating this set S is equal to the summation over all such paths, probability of all such paths. And then given a particular collection of observed such sets, we can then estimate the parameters of the model theta using log likelihood, the negative of the sum over the log probabilities of the particular set Si. Another architecture that goes away from this sequential nature is the set transformer, and which utilizes the transformer architecture as the base model and is based on the attention-based neural network consisting of an encoder and decoder framework. And it uses an efficient attention-based mechanism that reduces the complexity from quadratic time to linear in the sequence set length. And then this model is generally used to learn set representations, classifications, and sequence ordering. And one of the points mentioned in the paper is that previous architectures, when modeling sets, generally rely on pooling methods, where what you do, you pick up an multi-layer perceptron architecture and you process each set independently, and then once you obtain some feature representation.
Yeah, you have to get quickly to your contribution, no?
Yes.
A lot of time has gone.
Yes. Features, and then they're aggregated using pooling operations. And basically, since our architecture is based on the set transform, we'll explain this so that this is leading to our architecture.
We have time only until 3:30. Okay.
Yes.
Only till 3:30. Yeah.
Yes. So basically, the set transformer includes two operations: the set attention block and the induced set attention block. So if you consider two sets X and Y, and such that each element has its own d-dimensional representation, and each element is represented as a row in the matrix X and Y. So the multi-head attention block basically follows from the multi-head attention of the vanilla transformer architecture, where the only difference is that the multi-head attention block for this set transformer operates where the X is given as the query to the multi-head attention block and the Y is given as the key and the values to the block, and we are learning the parameters W. And the only difference here is the feed-forward network that has been used in the first stage is a multi-layer perceptron layer, which is only applied row-wise, so that each row is processed independently of the other. So when you say the self-attention block, so set attention block is basically the same thing, multi-head attention block, but the input that you pass is the same set X. So here the set X operates as the query, key, and the values. Another variant is the induced set attention block, which is used to further reduce the time complexity from quadratic to linear time. And here the block utilizes additional vectors I, referred to as inducing points. And this is similar to low rank projection, wherein a small set of vectors I are used to attend to vectors in X. And then the hidden states of these attention outputs are used as key and values to compute the attention using X as the queries. So this is the second variant of the attention induced attention. Now we'll move on to the R implementations. Afrin, you can continue.
Yes. So we first started by finding data sets which we could use for learning preferences over sets. So we would ideally want a data set which has pairwise or rank preferences over sets rather than individual items in the sets. So we came across this paper by Google which claimed that there are no curated data sets which actually have preference learning over item sets. There are many rating based rating based preference, not exactly preference, but recommendation data sets, but they are over items and not over a set of items. So we decided to go forward with this data set. So this data set is called CPCD, and it has it's a multi-turn dialogue dataset where the dialogue is between the user and the system. The user asks for a particular playlist based on some assumptions, like maybe they want rock music or some other presets. So the user queries the system and then the system responds. And based on the dialogue between them, uh, a set is so a set of tracks or songs are retrieved using a sparse or dense retriever, and then further this top k tracks are used to learn preferences by taking the feedback of the user. So this is the data set. Moving on. Next slide, please. Yes, so this data set contains 917 conversations, which are split into train and validation and test. So the data set is quite small, but then the number of tracks which are in the data set is quite large. So the data set has around 100K tracks, and this means that in the set learning task, the cardinality of the set is quite high as compared to the amount of data that is available for learning good representations of the items in the set. Yes, then within each turn of the dialogue, uh, there are user queries, system responses, and then search results, which are based on the words taken from the user queries and system response. And then the dataset also contains the liked and disliked uh, items, tracks from the based on user preference. So we decided to experiment with GRU2 set and set transformer. So the models proposed by the sequence to set generative model paper, they had one variant which used a GRU2 set and the other one which used pooling based MLP architectures. And because these models, in order to make them permutation invariant, utilize sampling in their training to compute the loss function, they are quite slow. So and because our data set had large cardinality, we were not able to run it faster. So we decided to skip over this, and we went forward with the set transformer base architecture. So in the set transformer architecture, we use IMAP blocks, which are induced multi-head attention blocks. They basically reduce the attention time from quadratic to linear. And then in the decoder, we use pooling based multi-head attention blocks. So this basically performs pooling over the multi-head attention output. And then further what we do is these transformers is like so it is set up to use a specific sequence length. So what we did was we came up with a pad token. So because in the data set we didn't have a context representation, a vector representation of the tracks, we decided to use one hot vectors, and along with that we added pad token so that as the data set had variable number of variable number of search results, the input to the model was variable. So we also included masking in this to compute attention only over the items which are actually in the set and not over the pad tokens. And then so basically we train this model such that we can think of this as a system where we have a recommendation system, and from a large set we get a subset based on some prior knowledge, and from that subset we use the model to find out what are the user's preferences so that those preferences can be given to the user. So in this case, we to the model we provide as input the retrieved search results, and then the task of the model is to generate a preference, a set which is the user preference. So this set should contain the subset generated should contain the items from the input, and also it should align with the user preferences. So for model training, we wanted to try DPO on this model architecture. So we first decided to train our reference model and then train the DPO based preference optimized model. So we first trained the set transformer using negative log likelihood. This is to increase the probability of generating the user preference, and this probability can then be used to optimize preference optimize the other model. And what we do here is that this is the negative log likelihood loss, and we only consider loss over the items which are actually present in the set and not over the padded tokens. Then we further use this model as a reference and train our DPO model using the following laws. So here theta is our model which is to be learned. This is the model that gives us the policy, and then we use the negative log likelihood train model as a reference. So here again, we only compute probabilities over we only compute the log probabilities over the items in the set, and beta is a hyperparameter, and then this equation is passed to a sigmoid, and then this is passed to a log to get the final DPO loss.
So one doubt, first
Yes.
you train a set transformer to generate the user preference and keep this set transformer as the reference model, right?
Yes.
So then DPO would be aligning to the set transformer, right?
Yes.
So then why should we need DPO? Like we already have the set transformer.
Yeah, so actually we wanted to see if a set transformer is capable of learning preferences. So, I mean, there are very less.
Actually, I'm very confused. You're trying to match the DPO to set transformer, and now you're saying you're trying to check if set transformer is capable of learning preferences. Very confusing. You're not training a set transformer to match DPO, right?
Yes, yes. So actually, this can be further. Because we did not find a lot of good data sets, initially our plan was to pre-train
No,
a
but
model and then.
you're not answering my question.
Yes.
Vishak's question was, are you trying to match a DPO to set transformer? Set transform produces the ground truth.
Yes, the set transformer is not really. Actually, in our results, we were not able to get the set transformer to produce good results.
No, but
And
here in this case, the set transformer is not generating the ground truth data. Ground truth data we already have from the data set. First, the set
yes,
transformer is learned to generate outputs. Like given a set of tracks and given a query, the set transformer is trained to output a subset of tracks that the user might prefer.
yes,
Now, this preferences might not be aligned. The model might not be guardrailed to give proper user preferences. Now, with DPO and the seed preference data that we have from the ground truth data, the
hmm,
data set provided by Google,
yes,
we now align our this we take this and this our learned set transform as the reference model, because that is what DPO does. The first stage is SFT, and then you take the SFT trained model as the reference model. And now using that model as the both, like initialization is basically the same. You set your theta as also the same learned model and the reference is the same. And now using the seed exemplars from the ground truth with a proper labeled preferences of one subset over the other. Now you train the model such that the model now has better preference.
So so you take the set transformer as a reference model, which is trained on the user preferences, fine. And then you're trying to match the DPO to the set transformer output, right? It's not taken as ground truth, fine, but you're trying to match the DPO to the set transformer output. That's still correct, no?
So
No, we are
why?
not. It
Yeah.
will be other way, right? DPO output won't match the set transformer output. The set transformer's output will be only rewarded when it is towards the output of the goal preferences. So it's like you are trying to update the parameters of the set transformer such that the reward that it gets for generating preferences is towards the ground truth preferences, and that's what DPO is doing, is restricting.
No, I didn't understand. Can you repeat once more? Can you
So,
repeat once more?
so I'm telling is that it's not the case that DPO is moving towards what another learned set transformer is doing. It is the case that the the reward that the set transformer gets after generating an output is maximized towards the ground truth preferences.
Yeah, that is okay.
Yeah, that's what is the case here, right? The ratio of pi theta
No,
over
what is the
pi.
connection with DPO? The reward that set transformer gets. Um, you're saying the reward, no, I didn't understand. The reward that the set transformer gets based on the ground truth is used to train the DPO.
No, it's used to train the. See, there are two instances here. The first instance is the reference model. The reference model is what your currently trained set transformer is, and this is only kept so that the new model that you learn does not go too far from this initially learned model. So this is the reference model is kept to keep that.
Fine, Sam. What are you doing with DPO? What is the connection between DPO and the set transformer? What is the connection between DPO and set transformer? We are running out of time. You
yes.
spend too much time. What is the connection between DPO and set transformer? Can you get to that point quickly?
Yes, so we can think of a set transformer as a language model, but instead of generating sentences, it's generating sets. So it might not be aligned to generate sets given a set which is aligned towards the user preferences. So that's why we use DPOs to align the model, the set transformer to user preferences, and this is better. Like this can be
Acha,
achieved
you're
by
using set. You're using DPO as an objective within set transformer.
yes, yes, yes.
Okay, so that's not the same as what Vishak was saying, right?
Yeah.
Okay.
Yeah. So actually, I think I should skip over some of the parts. So we had some interesting results on synthetic data set. So this data set actually had a lot of issues because of which we couldn't get good results. Can you move to the next slide? Yes, so actually we created a synthetic data set where we take integers from say 1 to 5 and 2, and then we use this, then we take a subset which is say the retrieved documents and or retrieved items from which a subset of those are preferred by the user. So we want to find that out, and in this case, as we have a synthetic data set, we decide that a preferred item would be a number, an item which is linked to a number which is divisible by 2. And the dispreferred items would be the ones which are not divisible by 2. And so we experiment with a set transformer on this. Next slide, please. So we get the following results. We see that, so one thing interesting that we noticed was when we use negative log likelihood loss, a lot of the times the set transformer would just generate one item sets, and it would not be correct. Like it would output odd numbers instead of even numbers, which are the which is the preference function in this synthetic data set. And when we train this model with using DPO without reference, we observed that uh, uh, even though DPO did not output a subset from the given input, it was inherently learning the synthetic preference function that we used. So in the output sets, it always gives even numbers. And when we use DPO with the reference model, which was the NLL trained model, the the model started performing way worse. So it gave worse results, as in earlier DPO without reference was able to
Okay,
learn
go ahead.
the.
Go ahead. We are on a lot of time. Just
Okay.
close it.
So, so
So
basically, you are saying with DPO the results were coming down. That's what you are saying.
yes, but we have another reasons to conclude why our experiments didn't work out. So we initially tried with the real data set, but it had a high cardinality on the set, but the number of training instances were very less. And we also went through the set transformer papers experiments, and we noticed that they have tested their model on feature rich data sets. So mixture of Gaussians, then point cloud classification, then image classification, image finding odd man out from a set of images. So these the input that is given to the set transformer
It's
is already
already
feature rich.
okay.
So in our case, as we had passed one hot vectors, I think the model was not able to decide whether to learn preferences or whether to learn set representations well. And yes, so there was
So,
a
so you're saying the reason is that set feature is data set failed to work because of fewer training examples and high cardinality of the top tracks. So you're saying the failure was not because of DPO.
yes, yes, it's
Ideally,
not
you
because.
would want a good reference model to start with to put the DPO objective in. So, and to get a good reference model, you need a lot of training to be done beforehand. Like in LLMs, we also see that we require the SFT before we use the DPO objective. And that SFT is basically done on a massive scale, not at the scale of retraining, but still at a scale greater than what
So are you
you do.
saying that it would have made sense for you to do DPO with set transformer after some SFT, but SFT was done, right?
Yeah, but
Yes.
the data used for the SFT was not at the scale that you would expect.
Okay. Okay.
But you were able to show that with the DPO, if you don't use the reference model, then at least the DPO is able to get what the preference function is in the case of the synthetic data. So that is one positive thing, that when looking at just the NLL.
Okay, fine. I think we'll move to the next presentation. I think you should not give up on this. However, if you can pursue this for a paper, even negative results are fine, but I think there must be something that will help us fix this. So perhaps we should discuss this separately. We'll discuss this
Yes,
separately, but don't give up on this, because I think your
yes,
seminar and here you have worked very hard. And
yes.
please check in all the code, okay?
Yes.
Okay, I think we'll talk about it later.
Yes.
Sure. Thank you.
Thanks. Jahnavi and please, Priya, bring up the slideshow. I'll just be back, bring some water.
Yes, sir. Speak. So this is our project, enhancing classification accuracy for questioning. We use the power of invisible refinement.
So you're still group of 2, right?
Yes.
Yes, go ahead, please. Go ahead, please.
Okay, speak. Either you, next. This is the problem statement. So we use consumer complaints, and our aim is to classify them on the basis of whatever information we have. So initially we don't have all the information, and we train a model so that we ask the right set of questions to get whatever information is lacking. So the motivation behind the problem is because the users want to complain. So, it requires a lot of processing behind that. So they cannot kind of, the process of consumer complaints, as we see in all of the customer care services or all of that, it's not.
Yeah, you can move a little fast. You can move a little fast on this.
Okay. So these are the data statistics. So we use, so you can see the representation between of the entire data set. So we have these classes versus the number of labels that are present.
Go ahead.
You see on the x-axis there are number of occurrences, and the y-axis you have all these class labels, you would say. The data set initially had 18 classes, but what we do is we combine the ones which have similar understanding. So for example, credit card and prepaid card, they have similar objectives. So we combine them, and eventually the data set has now 12 labels and the corresponding number of occurrences. 13 labels. Go ahead. Okay. The model architecture, so we use SBERT here. Now, we have two approaches. So the baseline is that the entire SBERT model is there. You fine tune you use the entire model and, find the vectors and fine tune all the layers that are present in SBERT. And the other one is you do not use the entire SBERT model. You just extract the vectors out of those and with the vectors that we have, we want the explainability. So the second approach is what we are trying to focus on here and compare with the baseline. That is the entire model, so all the layers together. So what we do is we freeze all the layers of the SBERT model and just train the classifier layer. And for word embeddings, we have TF-IDF and the vector size is about 27,507. Then we train a neural network to perform the classification task. And
can you go back? Could you go back? Okay. Good.
Yeah, so this is pretty similar. We fine-tune the layers of the SBERT model. So the embedding plus classifier layer, we fine-tune that. And all the other layers we freeze. So our aim is to extract the vector out of it and not use the entire one, because that is resource, that is time consuming and it requires a lot of compute. Okay, so we prompt the model for the question. So the information that is present already, it's not complete. So in order to get correct classification, we need the right set of questions to be asked so that we have that information which can help us classify the questions better. So for that we prompt the LLM. Okay. We are going to explain the experiment details. Okay. So after doing all this, we found that with the customer starting with half information, the accuracy achieved by the model is 38% only. And then when we used our technique, then we found that our results goes up to 75% when we use vector embeddings from SBERT. And when we use SBERT fine tuning, we achieve 77%. So this is the confusing matrices, and this is the results. This is the F1 score, recall and precision score with support for when we have used the SBERT embeddings. Okay, so this is our baseline. When we fine tune SBERT with Shapley values having the explanations, we compared that if we have the explanation with the help of Shapley values, is the technique which we are deploying will able to capture those or not, or this is whether it is efficient or not. So after training all these two types of models, we did some error analysis. We study what all the misclassifications are present there. So we find that before, if we just train the classifier and study the misclassification, we can see that with baselines we have this red bars shows the misclassified sample, and after our technique, it has been shown that there's a significant reduction in these three. I mean, in these two, there's significant reduction, but for these two classes, they are comparable. Okay, so what our technique are here? Also, there is some one word cloud where this one is for the Shapley values, and this one is for the explanations obtained by aligning vector. What is this? I will shortly see. So here we can see that it is able to capture more or less. I mean, I thought just a way to compare the important words. So here we can say that these two are comparable. Okay, so what we did to have the explanations, since okay, so we all know that after having the feature extraction, which is a fixed length vector of any length statement, say we have a 550 length question, we'll still have 384 vector. If our question is 54 words, then also we'll have a 384 length vectors. So there's a roadblock. So how to get back towards the statement from the vector? So we tried using vector alignment. Now what is this? So if you hear, we stated that we have used this much of neurons while training our network. So it is, yeah. So 27507 neurons we have used. So how do we get this number? Is with the help of TF-IDF vectorization. So if we do TF-IDF vectors for the whole data set, we obtain the vector length of 27507. So we thought, why not to with the help of that training only, why not to get transformed those 384 length vector to 27507, and then now here the BERT embeddings are also having 27507 and TF-IDF are also having 20507, and we tried to align those two vectors. Now how did, I mean, how, so after alignment also we trained, we again fitted the model and find the predictions, and we find the same results. Okay, it's around 74%, 75%, 74% only. Okay, so how did we align all these two vectors? So we started with centering. The first step is like centering of
The two vectors you're talking about are what? The two vectors are one for the document you want
one
to
is the
classify.
SBIRD embedding vectors we got from the SBIRD. Second is TF-IDF, which is completely explainable.
Second is what?
Right?
Sorry.
We have which is completely explainable. TF-IDF vectors, we know the corresponding words, right? We have in those dimensions represent the
TF-IDF for
word
what?
number.
For the TF-IDF for the class labels, TF-IDF for the question.
TF-IDF for the whole textual data set. I mean, in the
you
data
train
set,
a classifier model on the data set, you said SBIRD. Your approach is basically training a classifier model on the data set, SBIRD model fine tuning, and SBIRD embedding plus classifier. And you said have explanation from both the models. What are both the models?
First model is the fine-tuned one, which the whole BERT is used, and second model is feature extraction plus neural network. So in the second technique, we have a roadblock. Where to have the explanations? How to have the explanations out of those vectors? So
you're doing all this for explanations, is it?
Yes. For
explanations, I see. Explanations are for you're trying to align the embeddings with the TF-IDF vectors for attribution.
Yes.
Okay.
Yes.
Go ahead.
So this is our first step towards the alignment. So A and B are, A is the TF-IDF vector and B is our SBIRD vector. So we started SBIRD vector 27507 after the neural network, that trained neural network. Okay, so we tapped those vectors from there. So we centered it first. First we did centering, then we did rotation. So after rotation, we tried to decompose it. I mean, okay, first we did the centering, then we tried to, here we can see the outer product. Okay, so and then SVD. So what we are doing is we are trying for having one vector, the second vector plane is getting rotated to align. Okay, so with the help of SVD, we are having this rotation R is equals to UV transpose. So
Okay.
what rotation it would need to minimize the error, the R. Okay, so then we scaled, obviously the new vector will be scaled after the rotation, and this is our new rotated S-bird vectors. So with this new rotated S-bird vector, if we'll apply integrated gradients, so here two things are there. First is Shapley values. So Shapley values are the approximate explanations, and in the literature, the best working procedure is, the best explainability technique is integrated gradients. So with the help of integrated gradients, we got the important significant vector elements, and with the help of alignment, we find the corresponding elements, and those corresponding elements will tell us the important words. So that is how we got, and this is not at all resource heavy. I mean, I have done all this in my local PC instead of having bird trained for one night. We train on this. So this is what. So finally we get to. So while we do the literature review, yeah. So for this we've done the literature review and all these papers that we went through. Yeah, that's it. So we get to see that.
Can you show the explanation? Because you have shown, fine, the word cloud you're getting, also the word cloud you're getting is through mathematical modeling of through that vector alignment, is it? The word cloud, yes, for CI.
Yes, actually I have a demo, small demo. We have a small demo.
Okay.
Yeah. Okay, we'll show them. So Janvi, तुम्हारे laptop पे demo आएगा?
Can I assume your contributions are equal?
Yes. It's visible, right? So we together have all filtered data and all. So I think we need data and coded the experiments and have this done. So let me Okay, so starting with we tried. Okay, so let us say that we start with a half information that I have lost my debit card. So these are the generated questions. Can you please clarify
this is using what?
And how?
This is using what?
GPT-2.
We have hosted it somewhere locally, is it? Okay.
Yeah.
Okay.
We hosted it at Office.
Sorry,
we hosted it at Hugging Face.
Oh, Hugging Face. Okay, go ahead.
Yeah. So this is the question, and now we need to answer this question. So let us try to answer. Can you clarify when and how you noticed the issue? So yesterday, I found my card missing. Is there any additional information? What issues you are facing? I have some debit from my account. What issues?
Okay.
That's it. Let us see. So I think so it has classified into this class: credit reporting, repair, or other. So this we have accumulated from the various classes, since there were overlap between the classes. So this it has classified too. Let us try one more example. So as we said that we had 18 and we merged them to 13. So
No, but I really want to know what you see. That word cloud I want to see. All this is fine, but I thought the idea was that you would eventually have this word cloud shown, right? Some kind of explanation, explainability. I mean, your entire alignment. Where is the alignment output? I want to see the alignment output.
yeah, actually we have data frame for that, and we were thinking how to show the comparison. So actually with all these experiments in between, Aravat also was not working. So we haven't coded to show the real comparison, but we have that this data frames, but we haven't coded to.
Oh, that is okay. That is okay. That is okay. That is okay. I'm not looking for a fancy UI. I think Vishak, this is also fine, right? I mean, as long as you can show it in a spreadsheet, that's fine. So can you show? Can you show? I mean, I want to see that word cloud, that alignment in spreadsheet. No problem.
Yes, sure.
Okay.
So this
So
one
what
is
happened?
from S-Bird fine-tuned 5 important words, and this was after alignment. So let me
You're saying
close
this for every category or for every query?
for every query, one by one.
So these are different queries you had fired.
Yeah, the data frame, simple that original data frame. We go on having one by one.
The right one is after alignment.
Yeah, this is right. This is.
What is alignment? What is
This is with
alignment?
alignment. That our technique of getting extensibility, and this is from fine tune.
I'm still trying to understand what is the alignment you're showing here.
Actually,
So
this is not the alignment.
Hmm.
No, this is not alignment. By alignment, we mean to refer back from vector to sentence. So this is not word alignment. We did vector alignment. So sentence vector 1 is aligned to sentence vector 2. And what is sentence vector 1? Sentence vector 1 is the S-word embeddings, and sentence vector 2 is the TF-IDF vector embeddings. So the first one is with the baseline approach, and the second one is what we are trying to do.
First was the baseline.
Yes, the S-word
Left.
And the second one is
LHS is the baseline.
Yes.
Alignment using baseline. What is the baseline here? Sorry.
The S-word model. The fine-tuned S-word model.
And on the right hand side is alignment using your method, where you have also done.
TF-IDF.
So is it better?
Comparable, yes. I mean, see, if in the first method we are using whole
Let me
lot
show one
of
example.
that
Yeah, only 1
data.
minute left. Only 1 minute left.
Yes.
Show me one example when it is better. One
Yeah,
example it's
here
good.
we can see that this is completely comparable, right? So credit
Hmm.
card, account, bank, see credit card, account, bank, payment. So we can see the comparable thing. So that's why we try to have a
Where is it
workflow.
better? But where is it better and where is it worse? If you can show one example of better and one example of worse.
Yeah, actually, we should have done that. We haven't done We've explicitly this. not mentioned. We just tried to compare these two with the help of the accuracies we are getting, right?
So final
So
accuracies
we
were
haven't-
similar, is it? Final accuracies
Yes.
were similar.
Yes.
Which
So
one?
that is how we tried.
Which table? Which table? You had said accuracy achieved following
Yeah.
0.38704. GPT-2 with half information. Which table are you referring me to? Where it was better?
Yeah.
Can you go back to the slides? Visha, who's presenting next? Already 4 o'clock. Yeah. Visha, we just remind. Meantime, can you just
Sir, this one actually we haven't. I think this was already. This is just with the alignments. We haven't posted the baseline
Okay.
values. Actually, it was here. So, but we were not able to table it well. So
This is baseline.
discussion
This
with the
table.
Yes.
This table is baseline.
Yes, both are comparable, having almost same.
This baseline and the other one you should half information post questioning is what? 38%. No, that is 38%.
Post-questioning
50%.
No, this is with half information. So this is our alignment thing, and we started with when we started with half information. These are the result. And post questioning, after having the question and answer done, these are the results.
75. So you're saying 75 is
These
greater
are
than
the
74?
result.
Earlier,
Yes.
weighted
These are the
average is
result.
showing 74.
Yes.
So you're saying 75 is better than 74, and that's your improvement, right?
No. Actually, with SBIRT, it is 77%, and with alignment, we are having 75%. So almost, I mean, since SBIRT is resource intensive, right? So almost comparable.
So the fact that we are able to achieve even comparable accuracy with SBIRT is proving that the method that we applied is working pretty well with exponentially less number of resources.
So, but I should compare post questioning 75% with SBIRT 77%, right?
Yes. Also, we can have more experiments with much more data set to see how the extendability
And
is
how
particularly.
how faster is your approach, or how less memory intensive is your approach?
Sorry, how?
How less memory intensive is your approach, or faster is your approach?
Actually, yes, we haven't these on numbers, but since we all know that fine tuning a bird takes one night, and having the SBIRT feature extraction can be done in 2, 3, 4 hours if we have a good 15 lakh data set, say.
Okay. So in terms of training or in terms of inference, you're gaining?
In terms of training, yes. In terms of training.
How much time does yours take to do this alignment, the mathematical modeling using
3 to 4
centering,
hours.
rotation?
That center rotation and all hardly taken few minutes.
But overall takes 3 to 4
So
hours.
the
And SBIRT takes?
For overall experiment, for SBIRT we need one complete night, and for our alignment technique, it hardly takes 3 to 4 hours to do all the things.
Okay.
What is the SOTA work in this area? Aligning to, yeah.
Yeah, actually, yes, this is what is this state of the art. I mentioned, I think it is integrated gradients we used for explainability, and there is no SOTA for this since we cannot get back from S bar to sentence. There's no technique now. If we'll see, say, I can let you see that it is very unfeasible to get. If you'll ask the co-pilot
Vishak,
that I want to,
Yes, sir.
can you ask 6:30 team to come now because the next team has not come.
Yeah,
I
yeah,
want to
sure.
get
Yes.
back from word embeddings of. I want to get back from word embeddings of expert to the original. So it is giving something with Siamese. So okay, so this is giving one solution with the help of Siamese network. So this is not feasible until and unless we have a second pack of sentences, right? So it is almost
Right.
unfeasible to get back. Yeah,
Okay.
here we tried to have.
Okay, Resnik can get started. We have thanks. I think this is nice to have understood especially through your demo. Vishak, let's move to the next presentation.
Yeah, sure.
Sure, sir. Thank you, sir.
Resnik, can you get started?
Yes, sir. Yes, sir. So let me share the screen. So this is the report we have made for the project. So we have benchmarked multiple optimizers and implemented them. Now,
You're
like
alone, is
to
it?
benchmark. Yeah, I'm alone.
But you had a team members and they have not contributed, is it?
One of the team member, yes, like one of them left the course, like dropped the course, and one of them is not contributed, sir.
Okay. Who are the others? Sorry.
So the other is Adit Agarwal
Oh,
and
Adit.
like Muskan.
Adit Agarwal did not contribute.
Yeah.
And Muskan left the course, is it?
Mm-hmm.
Okay, thanks.
Yeah. So like so in this project, what we have done is we have benchmarked multiple optimizers like SGD, RMS prop, AdaGrid, and Adam. And for that, we have used MNIST dataset. Now, in the introduction part, like I've explained that we are what optimizers we are going to implement and benchmark, and then we have focused like the what are we going to implement and what are we going to benchmark. So these are like some of the details about SGDs. Like it uses single examples to train the model, whereas in AdaGrid, so there is like this exponential, like we divided with this GTI, and there is like the like learning rate is decaying here. In RMS prop, like the we have a weighted like squaring kind of a thing. So this is like weightage of, so we give higher weightage to the newer examples and lower weightage to the previous example. So in this case, like there is a problem, like in AdaGrid, there is a problem like it, like the learning rate becomes slow as after a long time. So this does not happen in RMS prop, but obviously it can happen after a very long time due to the accumulation of the like the this term. in Adam, what we do is we actually add the momentum also. So momentum is also added, and these terms are to correct the biases because we are starting with the zeros of the hyperparameters. So this is like the formula for that. Now the methodology what we have adopted for the benchmarking is following. So first there is a dataset selection. So we have used MNIST dataset. So that is like handwritten digit
B
recognition.
is a bit misleading. I mean, you mean I, right? You yourself have done it now. So others have not
Yeah.
contributed at all. So it's you, only you.
Yeah. Yeah. So in the dataset selection, like I have used MNIST dataset in which we have handwritten digit recognition. So like it's a classification problem among 10 classes. So for that, like first there is a data pre-processing thing going on. So like the output we have to like do the one hot encoding because at the last layer we are using softmax, so we have to like one hot encode it, and also we are normalizing the pixels between 0 to 1, and this is the architecture. This is a very fairly simple architecture we have used. So first is input layer and second is hidden layer. So it is only with one hidden layer, 250 units, and ReLU activation function. The output layer is of 10 units with softmax activation function. Now to train this model, we have used different optimizers. So first is SGD, second is RMS, and third AdaGrad, and last is Adam. And the loss function we have used is categorical cross entropy loss. And now for metric, we have used the percentage of the correctly classified images from which we can calculate accuracy. So we are using a batch size of 120 and epochs of 10. Yeah. So let's first go towards the result of this benchmarking. So results for the benchmarking are the following. So as you can see, like uh, Adam has a very high training accuracy compared to like uh, compared to RMS, sorry, compared to AdaGrad and SGD. So the RMS prop is like equivalent to Adam for this particular data set. So and for different data set, it can be different. But for this particular data set, the Adam is performing equal to the RMS prop. So these are the results we have found. And yeah, so like, yeah, so it takes a less number of time. So Adam takes less number of epoch to reach the um, to reach a higher accuracy as compared to other, which was expected. Now for the implementation part, we have used a very simple quadratic function, which is x square plus y square, and its derivative is 2x plus 2y, sorry, comma 2y, and its global minimum is 0, comma 0. So we tried to run multiple algorithms like Adam, RMS prop, and AdaGrad to see like how it is converging towards the global minimum. So initialization, first we tried to do randomly, but right now we have fixed it to 6, comma 4. So if we are going to change it, we are going to get different like we are going to get different number of epochs to converge. Now, so these are like basically we are calculating the gradient and then we are updating the moving averages of the squared gradients. So uh, like we are like calculating the average of the squared gradient and then we are updating the learning rate based on that. And we are like doing it for 10 iterations. We are doing it for 20 iterations. Sorry. So these are the graphs we get for the different trajectories. So as we can see, like the RMS prop is doing good and Adam is also doing good, whereas AdaGrad is not doing that good because like the slower learning rate at the end. So that is the problem. And now here also we can see that like the ADA grade is kind of a very, at this point of time, it has a very small like step size or learning rate, I can say. Whereas as compared to RMS Pro and Adam are fairly large. Also, we can see the Adam still have a very large learning rate. So, I mean, it is the learning rate is not converged or it is not like diminishing, as I can say. The conclusion is that like Adam and RMS crop gives a very good result, as we can see, and like as compared to SGD and the ADA grade. So this is the code for the benchmarking and the implementation. So the first is this MNIST dataset. So we have loaded this MNIST dataset and categorized and normalized it, then printed the dataset, and then this is for the training. So we can just give optimizer, name of optimizer, and this is going to like train that from this model from that particular optimizer. So here we are choosing SGD, RMS prop, and Adam. So we are like taking loss, accuracy, validation loss, and validation accuracy. So all these things we are like storing to plot that to get the conclusions. Now here we are doing the training. So as you can see, train MNIST. So here we can just give optimizer name, which is in this particular list, and then it is going to train, and we are going to get like the training accuracy and the validation accuracy and all the 4 parameters which we can plot. So here are like the 10 epochs. And here we have printed the accuracy of the final at the final epoch. Here you can see the graphs. And this is like the implementation part. So this is our objective function and this is its derivative. So like in like RMS prop, like what we do is we basically uh, like for the number of iterations, we just calculate the derivative, and then like there are we have two variables, so we have to update like the 2 times. So x and y we have, so we have to update the x and then y parameters. Now here we are storing the gradient of the first. So we are storing the square of the gradient of the first, and then we are, so this is like the gradient of the current, and then we can just multiply it with 1 minus rho and rho. So this is RMS prop. So in this RMS prop, what we do is we kind of give weight to the newer and older square of gradients. So this is what we are doing here, and this is just like dividing it with the square root of the square of the gradients, and one. So this is just the epsilon. So if it goes to 0, so this is to handle that particular case, and this is to update the value and to and then store that particular new solution in that array. So this is like solution evaluation, because so like we can give uh, like the solution we got from this particular iteration, give it to the objective function, and we are going to get the value for that particular uh, like the x and y coordinates. So these are the x, y coordinate, and this is the result that we are going to get. So here you can see the RMS prop reaches to 0.4 and 0.02 in 19 iterations. Sorry, in 20 iterations. So in ADA grade, this is same thing, but here we are just adding the square of gradient. We are not like giving the weights to it. So this is same thing. And here we can see that it is reaching only 0.4 and 0.2 in 20 iterations. So it is performing poorly as compared to RMS crop. Also in Adam, so there are 2 things first is we are storing the square of gradients, and second we have momentum also. So momentum we are storing it in m of I. So we can just take so this is mi and this is mn. So because we have to remove the bias from the 0, so we have to divide it with 1 minus beta 1 to the power t plus 1. So this is for that, and then we just like use the formula for the RMS, for the atom, and we added the epsilon here also. So to like to overcome the division by 0 problem. So here also, so as you can see that the initial point for all these things is 0.6 and 0.4. And we are running it for 20 iteration. Alpha here is 0.02, beta 1 is 0.9, and beta 2 is 0.999. And this is the result for the atom. And at last we have plotted all of them in one graph, and here also to show that how the learning rates are changing. Hello.
Okay, thanks, Asnik. So one question I have.
Yes.
So the same comment you have about Adit Agarwal and Muskan, who I think they were part of seminar also, right, with you? At least
Yeah,
Adit
yeah.
was part of seminar. So in
Yeah,
seminar
that was
also,
fun.
seminar also contribution was uneven.
I mean, it was. I mean, it was okay. Like he done like the part that I've given to him. He has done
The
that.
seminar it was 50-50, can I assume, or skewed?
I mean 60-40 you can say, but it's like it's equal.
But here it is 0, right?
Yeah, I mean I asked him to write the report, but like he didn't write that also.
And Muskan
So I
was
have to
0,
do
right?
it at the last time. Muskan, I think he has dropped the course.
Okay. Okay. So the Adit will not get any marks at all for the project based on this for the end project, right? The 0 contribution.
Yes.
Okay. Thanks. I don't have any more questions. I think I asked you a whole bunch of questions earlier.
Yes. I mean, I could have done more like complex project also, but like due to the time constraint and like I don't get enough support for that.
Mm-hmm. Yeah, seminar was on what topic? I just tried to dig up.
Seminar was on LLM, so RLHF kind of a thing. So we
Okay,
have
okay.
to.
Okay. Then only one question I have. The validation accuracy on MNIST you showed, and then you said that RMS prop was kind of the same as Adam.
Yes, sir. This thing. Yeah, because
But
it's
Adam picks up
overlapping.
faster. But Adam picks up faster, right?
Mm-hmm.
And what happens to Adagrad here?
So Adagrad here also picks up fast, but like after multiple epochs, like after 10 epochs, it does not reaches the same training accuracy. Here it goes very fast, and then it kind of
Okay. So
slows down.
is it because learning rate becoming small?
Yeah, that's what I expect, because in Adagrad the learning rate is a diminishing
Okay.
in SGD also.
Yeah, Vishak, do you have any questions?
No, sir.
Okay. Thanks then. Vishak,
Thank
so Rustic, your presentation was at 4, right? Was scheduled at 4.
It was scheduled at 6:30. So
So who was it at 4?
4 was Deepankar, but he didn't join.
Acha. Okay. Only Deepankar? Was there anyone else?
No.
Okay. Thanks then.
thank you, sir.
Thank you.
4:30 is by the team who mentioned they have internship or something, but later they message they will try to join.
They have the internship, but we have already changed their time. Acha, that one of the guys had internship, not everyone.
Yeah.
I mean,
So he
I mean,
later messaged me saying he will try to join.
I just messaged them that we are available. I'll just pick some water and come.
Yeah, sure.
Okay. Then we are Are they joining?
Not sure. Hi.
Yeah, Prof. Aditya. Please go ahead, Aditya. You can start your presentation.
Okay, sir, I will be presenting. I will just share my screen.
Yeah. So 3 of you have worked on this project together, is it?
Yes, sir. Sir, can we start?
Yeah, please go ahead.
Yeah. So basically, sir, our project was working with fine-tuning LLMs. So we started with a spin paper that was using.
So you don't have a presentation, right?
No, sir. A presentation like the recording.
Okay, go ahead.
Yeah. So our project was basically fine-tuning of LLMs. So there are two methods that are used basically that were used before spin. Those were RLHF and DPO. And spin was the third method that was in the literature, and that worked on the basis of game theory, where we can, like the GAN theory, that we compete the two models to make them better. So we found that in the spin original paper they were only using random sampling, and they were not using like a curriculum learning technique where we should give easy examples first for the models to compete, and then the hard examples. So they were not learning, like in the beginning only, if we gave the models the hard example, they were not able to differentiate and improve on that. So we try to incorporate the curriculum learning by taking into account hardness. For hardness, we use the length of prompt as a parameter to signify that this prompt is harder than this. Then again, they were doing random sampling and they were taking all the batches. So what we did was we tried to use co-research selection, like the chords. We took the chords basic code, and then what we did was we used the facility coverage thing from Apricot to select the batches that would be most helpful to us. And again, this helped us to generalize the diversity of gradients.
So what you have picked
Yes,
up is a adversary robust LLM fine tuning using curriculum learning. Is that the key? So when you say spin, and spin is based on two models, making them compete to make it better, right? So
yeah. So
but you
I
talked
will
about two
just
things.
yes, sir. So
So what
basically,
are these the
we
two
are
parts? Curriculum learning and
we have sir basically done three things. Like our contributions are like incorporating curriculum learning, and then when we have incorporated curriculum learning, we make the batches according to curriculum learning. Then we are using co-research selection to select which batches should be trained upon and which batches shouldn't be trained upon. And then we are in these batches, we are adversarially attacking the batch, like changing the prompts and then training the large language model to give appropriate responses.
adversarial training is but
Like,
spin is
I
also
can.
adversarial training. So course set selection for optimizing spin, and then adversarial training is also part of spin.
Yes, sir. Like we can see this. Like this is the basic spin algorithm, where we'll just generate output synthetic data via a dash from an xi prompt, and then we'll try to improve upon this objective function that comes from spin, and this gradually improves the model. What we have done is we have first incorporated curriculum learning, that the prompts should be according. We have
Wait,
ordered the
so
data set
wait a
in.
second. Wait a second. So
Yes.
this base self-play fine-tuning, that is basically the spin idea.
Yes,
So
sir.
that's the first thing you've done.
Yeah, that was we chose a different model and a data set, and we started with that.
So that is curriculum learning. I'm really confused.
No, what they did was they didn't order the prompts in any order, and they were taking like one in the same batch. They could have a prompt of length 10 and a prompt of length 100 also. So there would be a lot of padding issues. so the model wouldn't be as appropriate. Because the padded tokens would also contribute to some things. So what we did was order the data set first, so that similar length prompts are together, so that so that the model can learn appropriately. The padding, it doesn't have to learn too much.
I see. And now I'm just coming back to this their algorithm. They just, so this is basically adversarial learning, right? What you're showing in algorithm one is adversarial learning.
Algorithm, no sir, algorithm one is the base, like the spin idea that they present in the paper. The
what is the idea there? Synthetic data, then update theta t plus 1. 2-player game. Distinguish the response of the responder, right? LLM, those very human. Distinguish. Wait a second, no?
Yes.
So, what is synthetic data that is coming from LLM, no?
Yes, synthetic data is coming from
Okay, so
can I go step by step, over the algorithm, sir? I guess that will make it clear.
Yeah, sure.
So like what we did was we first took a prompt data set that we have prompt and response data set. That was ultrasat 200K we took. And then we first selected 1000 because of compute limitation, 1000 responses. Then we ordered these 1000 responses.
Your screen is stuck, maybe you're showing algorithm.
Yes, sir. What I am in this input part here, that for this input part, the SFT dataset that we used was ultraset 200K. Then first what we did was we first ordered the dataset in increasing order of length of their prompts, like the prompt length. And then we batch the sample so that similar length prompts are in a single batch. So and then we pass the whole batch inside the facility coverage thing, so that our facility coverage thing basically takes which batches have similar representations. Like it tries to see which batches are varied enough, represents the whole database. So it gives us the indices of the batches that we should use. And then after having got yes.
This is spin, not spin, right? What is this?
Yeah, this is not. This is our, like, this is the algorithm that we have built, like the different final spin that we have built.
Okay, so subset obtained from facility cover. Okay, and then generate adversarial prompt and generate synthetic data. But this is a spin idea, right? Adversarial prompt and synthetic data, no.
No, adversarial prompt is not a spin idea, sir. In spin, what they are doing is a spin. The basic spin idea is here, sir. What they are doing is they are generating a synthetic response from the LLM, and then they are trying to minimize the difference, so that they can the data distribution of the SFT data set, the LLM data distribution comes to as close as possible.
So that's the same thing, no? In algorithm 2 also, like spin line 5 generating synthetic response, right?
Yeah, but sir, the input is here. Input is the adversarial prompt, sir. It's not the original prompt.
Achha.
So we are inputting into the model an adversarial prompt, but we want to ensure that, okay, if the adversarial prompt is like, because it's only slightly different, it should output the same response. Like, means the difference should not be too great to an extent. We are trying to ensure that, so that the solution, like the LLM parameters, are generalizable a lot more.
Can you repeat what makes the LLM parameters more generalizable?
Because here the prompt that we are using is not the original prompt, it's the adversarial prompt. And adversarial prompts, we are like, it's in the attack thing, we have given a perturbation limit that okay, it can go up to this limit and it can go up to like to and fro to this limit. So because it's not the original prompt, it cannot overlearn. Like sometimes it would be like the tokens will be shifted on the decreasing side, sometimes on the increasing side of vocab. So it's because we are inputting into the LLM adversarial prompt, the it has to the parameters have to change in such a way that the synthetic response generated even after the input of an adversarial prompt are as close to the original data distribution, like original ground truth.
So this
Because
adversarial, yeah. So this
yeah,
adversarial
please.
prompt is how different is from the like original prompt? Is it like some words being meaningless or
Yeah, what
spelling mistakes? Yeah.
yeah, like what we did was we did a PGD based thing. We couldn't do a complete PGD, so like we did a PGD plus FGSM mix kind of thing. What we did was we found the gradients of the output of
PGD
our
means what?
generated response.
Projected gradient descent. You mean
Projected gradient descent, yes sir, yes sir. And fast, like, so what we did was we took,
PGDN, what did
yes,
you say? PGDN?
FGSM sir, fast gradient method.
Ah.
That only takes in the sign of the thing and not the data, gradient data.
Right.
So what we did was we first found a loss between the true ground labels and the output that our model was giving. This is the cross entropy loss. And then we found out the logits with respect to the inputs, like the input what we should have. And then we clipped it, we found this data, and then we normalized it with respect to the length of the token set, like length of the sentence, the output tokens, so that we can generalize it. Because in different cases the output length would be different, so we wanted it we wanted this gradient thing to be generalizable across means that normalized across all stuff. So we divided this by length of the sentence, output sentence that we are having, and then we clipped it to a limit delta that we have set, and this gives us eta, and then that eta is what we are adding to our prompt, and this goes on continuously.
Wait, I'm trying to understand. Can you just repeat this once more? So you have generated adversarial prompt, generated state data based on that. And what are you trying to do? You're trying to do fine tuning of LLM. The attack.
Yeah. Okay.
Attack
So
is using
this
some perturbation. Attack is using
yeah.
some perturbation.
So basically, we are trying to find out the direction in which the loss increases a lot more, increases the most. So that the loss in this case is a cross entropy loss between our true labels and the output data generated tokens, between these two token sets. So we in the compute gradient step, we find the direction in which the cross entropy loss will increase the most. Then what we are doing is we are then projecting it into this. We are then seeing that how much different is it from the original prompt. Adding like this x plus eta we did, we'll find an eta here. Now we'll see that is this eta a lot different, because if it completely changes the context or
But
completely changes the
why
word.
is the projection step important? Why is projecting important?
Projecting is important, sir, because we don't want like the prompt is completely different. If we are like giving two completely different prompt, like who are you and what is this place, we cannot compare the responses then. So we want that it should be within an L2 ball limit or cosine similarity limit. We
So
search the
sorry.
literature, so that
You're projecting so that I didn't understand. You're projecting so that
the prompts are not completely different. That our input prompt and the adversarial prompt have some relation, have some similarity, because it shouldn't be that our input prompt was who are you and our adversarial prompt becomes what is this place. Their answers are supposed to be different. We want the inputs, suppose the input is who are you and the output is who is you, output becomes who is you, then okay, this is the thing that the LLM should be able to handle. So we are
Right.
projecting so that the LLM, the prompt that we are using is not totally out of context of the original prompt.
So delta decides the size of the L2 bolt.
Yeah, delta decides here. Yeah. Basically, we could have used instead of L2 some other also. Like we tried on entropy, but there was like the second order entropy thing, but we were not able to accomplish that thing because like there was some calculation errors. So
You tried
L2 norm,
you also tried
entropy ball. Entropy we tried, but we couldn't like get like the whole thing. There was some errors and we couldn't fix it, so we stuck to the L2 ball thing.
Okay.
So then how did you select delta?
Delta we selected based on the vocab size. In the basically there was a paper that how we could use PGD for jailbreaking prompts, like jailbreaking prompts, and in that they said that we could use a length of vocab size divided by length of average sequence, and like there was some formulation. So basically length, it's in our case I guess it's 50 tokens here and there. It can be like the tokens we are using, that can be 50 here and there in the vocab.
So the delta value was 50. That's what you're saying.
Delta value was 50. It depends on the vocab size basically, and how much you want to attack. So vocab size, and I guess the length of the token set. Like here we normalize it with the length of the sentence. So here we'll normalize with length of the sentence, and using that and dividing by some pi or some factor, we get this delta.
Okay.
Okay.
And the results that we achieved were there. Yeah, this is blue score actually. Like I just made a writing error. So in the first experiment where we didn't do anything,
attack is used within self-layer fine tuning. What is the connection with base self-layer fine tuning? Then you're not using base. Okay, you are not using base at all. No?
Yeah, we are like the loss function from the base we are using, but we are not using it at any other place. The methodology of the base that two players are playing against each other we are using, but for an adversarial prompt. And the curriculum learning and facility coverage thing is here, is used for the input formulation.
So methodology of the base, which is 2-player, and second is loss.
Loss function, yes.
Okay. And now you have curriculum. Where is it?
Curriculum learning, sir, basically in the input data set, what we did was for the data loader, we first turned shuffle to false and ordered all the prompts according to their lengths, and then made them into batches so that we can have similar length prompts in similar places. Our measure for hardness, like I mentioned here, is length of prompt. So we'll first get the batches according to which.
Just a second, can you go back?
Yes.
What is it? I think
hardness we have said is length of prompt, proportional to length of prompt.
I see.
This was used in this paper, so they told that it works and they were getting good results, so we thought we can use it. And then once we have made the batches, then we are
you're sorting basically based on hardness.
Sorting based on hardness, and then we are making the batches for the data using the data loader, and then we are passing the batches in the this facility coverage objective and seeing which batches complete cover the whole diversity of things, and then those indices of batches only we are passing it to the model, and rest we are leaving.
I see. Okay. So this facility location basically used to be.
So facility location basically selects those indices within a batch, right?
No. In our case, we are passing the batch gradient and everything as a distance. So it selects the batches like which this batch has higher gradient, this batch has lower gradient. So it selects the batches which you should input to the model in our case.
So then curriculum learning, what is the point of curriculum learning? Like we are
maybe that is
anyway,
maybe that is their curriculum learning. I think their curriculum learning is line 1 of algorithm 2. Is that correct? Your curriculum learning is within that. No?
Yes.
Yeah. So like
Or
after getting,
is there any other?
yeah.
Can you just answer yes or no? Is there anything beyond line 1 of algorithm 2 which is curriculum learning?
No, sir.
Okay. So is it correct to call it curriculum learning? I mean, I appreciate your work, but it's because subset in facility coverage. So you're sorting them as well, is it?
Yes, sir. Like after facility coverage, we'll get all the indices. So that those indices we like, suppose I get 3, 5, and 2 as the output. Like these batches should be passed. So first I will pass 2 because I know that for the batch 2 the prompt size is small and this is easy to learn. And then I will pass the batch 3rd, and then I will pass batch 5.
Acha. You have not mentioned it, but it's just simply length. Okay, so
yeah, it's in, yeah, like we have more only in the batching side we are here. For the curriculum learning thing is taking place because we are passed, the batches are ordered, so we'll pass first the batch that is smaller in length, that is selected and that has smaller length prompts.
okay. Can you just show the results once more?
Sure. This is basically a blue score. It's not blue.
So what is experiment? Actually, these are just different random runs.
No, sir. Basically, in the experiment 1, we are just using the pre-trained model. We have not done any fine tuning and seeing the blue score. In
So can you,
experiment
okay,
2,
just show all of them together. Okay, that is better. In the first
yeah.
experiment, pre-trained model. I see. Go ahead. And then
In the second one, we have the adversarial perturbation. We are attacking the prompt and seeing what the blue score is. So the blue score decreases. In the third one, we are training using spin on the base model, but no adversarial attack. So we see that there is a significant increase over the experiment 1.
So wait. So in the first one is fine. Second one, you added what spin? You have added what? The second one?
No, second one, we are just attacking the model. Adversarial baseline we are creating.
From algorithm 1. I'll go 2 and 1. I'll go 2 and 1. I'll go 3. Sorry.
Yeah, like now the prompt input is adversarial prompt, not the original prompt. In experiment 2, that's just the difference.
And then in 3, what do you do?
In 3, we are what we are doing, we are taking experiment 1 and then running the spin algorithm, but no adversarial attack, only the basic spin algorithm, the algorithm 1 thing.
Without attack.
Without attack.
And in 4th experiment, facility coverage. This is where there's a 4th experiment 1 plus experiment 3 plus curriculum.
Experiment 3, no, curriculum is in this also. So curriculum we have incorporated in all. In experiment 4, we are also the facility coverage thing, which subsets we should choose, because first we are choosing all that you can take all these subsets, the first few subsets only. Now we are selecting the subsets based on facility coverage, not random sampling.
Achha, so 1 is base plus curriculum, 2 is base plus attack from algo to,
base
and then 3, and then
3 is base plus spin plus curriculum. 4th is
No, in 2 also
plus-
there's curriculum. No? In 2 also there's curriculum.
Yeah, 2 also curriculum. Yes, sir.
Yeah, and then 3 is base plus spin.
Base plus curriculum plus spin. 4 is base plus curriculum plus facility coverage plus spin.
Wait, I'm just making in my note. And there's
Oh.
curriculum even in 3, right? You could
Yes,
write it, like you can present it a little better. Okay, and the 4th you have experiment 3 plus curriculum. No, experiment 3 curriculum is already there. What is 4? 4 is experiment 3 plus
Facility coverage, sir.
4 course set. Okay, and then
Course set.
5 is what? 5 is
5 is the final, like attack also incorporated. So here we are adversarial robustness.
Is it 5? 4 is experiment 3 plus what? Plus course experiment 4. 4 is experiment 4 plus 5 is experiment 4 plus
attack. Experiment 4 plus attack, and now we are not basic.
But already 4 had experiment 3 had attack. Na? Acha, spin without attack. I see.
Yes, sir. These two didn't have attack. 5 will have attack, sir.
Okay. So now I'm trying to make sense of the results. And so certainly experiment 4 is doing the best.
Also, sir, wait. In experiment 5, we are evaluating against adversarial prompts. So this is like we should compare with experiment 2, because experiment 2 is the adversarial baseline, and experiment 5 is the adversarial like robustness that we have achieved. These all are again normal prompts. We are not attacking in experiment 3 and 4 in the evaluation stage.
In 5 you are saying experiment 4 plus attack. In 2 also there is attack.
2 is yes, but in evaluation stage, in experiment
what is
2
the
and
only
experiment
difference?
5,
Only difference between 2 and 5 is only difference core, right? Only difference
no,
between
sir,
2 and 5 is core set.
No,
Core set is certainly a difference.
Code set and spin, sir. In 2 is just the basic. In 2 we have not done any spin training. Basically, experiment 1 and 2 are the baselines for our cases. In experiment 1, what the LLM plus curriculum is giving. In experiment 2, what it is giving in case of adversarial, like the prompt is not the original adversarial evaluation. If we are giving slightly perturbed prompts, so what blue score it's giving. In experiment 3,
no, wait. Experiment
yes,
experiment 1 and 2 are baselines. Experiment 4 and 3 and 5, the comparison is basically core set plus spin. Experiment 3 and 4, the difference is
facility coverage.
Core set.
Core set, yes.
Okay. Can I assume only one of you are speaking? Is the contribution same from everyone?
Yes. Contribution is same. Like they are at like one is in the office, so he cannot speak.
Okay.
So experiment. Yes.
Yeah. Go ahead. Sure.
So experiment 3 doesn't have curriculum learning, right?
No, all experiments have curriculum learning. Just experiment 3 is base plus curriculum plus spin.
Okay.
In experiment 4, we are introducing the core set, and in experiment 5, we are introducing the attack. But in experiment 5, our evaluation is also in the robustness thing. Like in evaluation time, also we are using attack. In experiment 2 and 5, at evaluation time, we are using attack. In experiment 1, 3, 4, we are at evaluation time, we are not using attacks.
Okay, fine. So I think the best result you're getting is with experiment 4. Obviously, you should run multiple runs. I don't know how significant it is, but looks like spin is not helping. Also, attack is not helping. Is there a conclusion? Because experiment 4 doesn't have attack, no?
Yes, sir. It doesn't have attack.
So attack is not as much helping, no?
But sir, in 4, the evaluation also doesn't have attack. In 5th experiment, the evaluation also has attack.
Also, that evaluation has attack. So therefore, it is apple-orange comparison, man.
Yeah, like we should compare experiment 2 and 5 and experiment 1, 3, 4. Because experiment 2 evaluation has attack, and that is the baseline. And
experiments 2 and 5.
And 5. Yeah.
Experiments 1, 3, and 4 are comparable. Okay, none of the others. Okay. So you should present them in different table.
Okay. Yes, I think.
I mean, same table, then you will kind of compare it against one. 2 and 5, okay, there's a clear difference. And 1, 3 and 4. Okay, at least when 1, 3 and 4, the difference is all of them have attack. No, all of them don't have attack.
Don't.
But core set is making a difference. Okay.
Yes.
Okay, then I think we have to end. Now we have next team. Well, where's the next team, Vishak?
Sir, like we have just mentioned the paper for chord. If we have used the chord string, like we have to mention anywhere else about, like before
No,
if we
that's
put
okay.
it on GitHub.
So actually, I'm very happy. Can you guys? So I think Pratik. I don't know, Vishal, if you're interested, certainly, but Pratik is doing something very similar. So can I request Pratik to reach out to you guys?
Yeah.
Because I think you should certainly write a paper on this. Okay. And then we can provide you compute also. You guys are all doing your BTech?
Yes,
Yes,
sir.
Yes, sir.
Finally, we'll be entering, sir.
Okay, so can you please work with Pratik on a paper? Because we're doing
Yes, sir.
something very similar, and I think a good paper can come out.
Yes.
Sure.
You're all available, now? Fourth year is done, or fourth year will begin?
No, we all will be entering fourth year, sir, now.
Yes.
Okay, you're entering fourth year. Okay, so that is good, na? So you have appetite for writing a paper now. But this is, I'm actually quite happy. Good. Vishak, anything else? I think we should move to the next presentation. It's already 5:01.
Nothing else.
You guys have anything more to present?
No, sir. Like it's like you can see the responses that because we got the responses like for comparison, like the ground truth. This is the base LLM, and this is like, is it visible or should I zoom, sir?
Yeah, I can zoom in. And Vishak, in the meantime, just next team, you ping them.
Yeah.
The next team, na? Yeah, go ahead. Ground truth first response. You did all this on Hugging Face?
No, sir. Like we had our R&D server, so we could use one GPU that our profs allowed. So we use that.
Oh, who in E department is it?
No, we use PTJO Team Ham's server for like one server, like Pranav's server. DGX6, sir, basically.
The DGX.
Yeah. Like, and the last one, like our final response after 3 iteration, like the ordering is there and it's like covering all the things.
Okay, this is the best of them. Okay. This is good.
Yes.
Yeah, but I think we should really take to a different level this work.
Yes.
Vishak is the next team joining. Who's the next team?
Haston.
So Haston, they said they will join, no?
Yeah.
We scheduled it to 5 so that they can join. So they should join. Yeah, we scheduled the whole thing. Okay. And Haston also had said 5 p.m. I remember. Okay, thanks then. Thank you. I think we'll wait for the other team.
Thank you, sir.
Thank you.
Thank you.
Vishak, can you join? Can you call up Haston?
Yeah, sure.
So you guys, okay, they have left. Okay. I don't know how to respond to my own message there. My teams have responded.
He will join now.
Yeah, Hastin, can
Hello,
you please
hello.
get started? Yeah, we run out of time.
Yeah,
So
yeah.
Hastin, please start because we are very much sticking to
Okay, okay.
time. So
Sorry,
your,
sorry.
your clock started ticking at 5 o'clock sharp. Yeah.
Okay. Just a second. I'll.
Please start the presentation.
Yes. Can you see my screen?
Yeah.
Can you see my screen?
Yeah.
So can I start? Hello.
Yeah, you
Yeah,
can start.
yeah, please.
Yeah. So
So can you show the first screen? First screen. Who are the people in your team?
my teammate is Niyati. She's here with me.
Hello.
Okay. So I'll assume your contribution is equal, right?
Yeah.
And contribution to seminar as well, no? It's equal.
Yeah.
You were together in the seminar also.
Yeah.
Yeah.
Machine unlearning. Go ahead.
So I'm just saying that during the seminar we had you had proposed another topic, but we could not do that. So we switched to our original topic that we had given an abstract and proposal initially for.
Okay.
Okay. So I'll just start with machine unlearning. So machine unlearning is the task where you have to you're given a data and a model trained on the data, and now you have to output a model, and you have some data you want to be forgotten. And now you have to output a model which has forgotten the data to be forgotten. So say currently the prime minister is some person A, and now due to some random event something occurred, and now the prime minister has changed to B. So now you want your model to forget that the data was A, right? You want some way to make the model forget the data was A, or say for privacy reasons someone's name was associated with a face or a image or something, and now you want that to be forgotten. So this is another case example where this problem may occur, that you want the model to forget some data. So that is machine unlearning. So there are two basic fields of two basic types of machine unlearning. One is exact and another is approximate. By exact unlearning we mean we just retrain the entire model on the data set minus the data to be forgotten. So it's that difference. So we just
So
forget
I can't see the slide is stuck. Why is machine learning? I can only see that.
Yeah,
slide.
I have not changed the slide, so I'll just go ahead. So these are some of the topics I was just saying: improving security, enabling adaptability, privacy protection, approaching the problem.
Just a second. I see. Okay.
So I'll further. Should I go ahead?
Yeah, go
Is
ahead.
it fine? Yeah. So defining the. I'll go to the definition of the problem. So this is just our proposal. I'll get to this later, anyways. So I don't want to waste much time. So yeah, I'll just get to the problem definition. Sorry for this. So we want to remove the influence of some training data. So here, just for notation purposes, let U be the unlearning function. So you take some model AD, that is the original model. A of D is the original model, D is the original data set, and DF is the data to be forgotten. So U of AD, D and DF gives a new model with some parameters by effectively removing the DF dataset from the training set. So we want to
Learning
output
algorithm is A.
another model.
Learning
This
algorithm
fine?
is A. Yeah.
Yeah. So we will split the training data into forget set and retain set. Retain set is just D minus DF. So we want to minimize influence of forget set data points on the model. Yes. Shall I go ahead? If you have any doubts, just interrupt me. Hello, am I audible?
Yes, you're audible.
Okay. So formulate the problem. So what do we mean by influence of the point? So we want to remove the influence of the forget data points on the model, right? So influence can be just Z star due to the points in the forget set.
Right.
So you can model this as the influence. So this is the influence. The challenges in these models, in this problem, is that the models are often very complicated, especially deep models and such, and so it becomes a bit difficult. And the exact machine unlearning, which is the naive retraining method, you just retrain the model on the data set minus the forget set. that is a very computationally expensive, because if you training takes huge amount of time, and you can't just to forget some small amount of facts, you don't train the model on the entire data set again. So that is the computational cost. So these are some of the challenges. So as I said, the first method is just naive retraining, and this is the ideal solution to this problem, where we just retrain the model on the data set minus the forget set. So we look at another approach called fine tuning. So in fine tuning, we train the model on the retain set. So we basically find the retain set, and we train the model for a few number of epochs just on the retain set, and hoping that trying to learn the retain set better, it will forget the forget set.
Right.
So this is of course of lesser quality than exact unlearning, but it is much more efficient, and we can it is computationally feasible. So this is just the formally we can define it this way. So I'll again not waste.
No, I actually can understand. Wait a second.
Okay.
No, fine tuning looks exactly like naive retraining. What's the difference?
No, retraining means from scratch you'll have to train the entire model on the retain set. While fine tuning means that you take the trained model on the original data set D, and then you just train it further on the retain set for a few epochs. So it's not retraining the entire model from zero.
So,
It is starting from the original learned model, the A of D, and then training it a few epochs on the retain set.
Okay,
Does
but
that
the forget set is very small compared to the non-forget like retain set. Fine tuning would
we'll make
definitely.
that assumption that the forget set is small, because if the forget set is very large, then the model will probably lose much of its capability, in the sense that it might not learn anything at all if the forget set is say 80-90% of the data set.
So the assumption is forget set is very small compared to the retain set. So then the fine tuning would almost take the same time as retraining, right?
No, why will the fine tuning take same time as the retraining?
Because the forget set is very small compared to the retain set.
No. The point is that in fine tuning, the majority of the learning has already been done. It's like the model will be trained on say 1000 epochs. So that 1000 epoch training is done. We'll just run it for 1 or 2 epochs on the retrain set. In naive retraining, we'll run the entire 1000 epochs on the retain set only.
Okay.
So that is the difference. Is that all right? I'll move ahead then. So
sure.
So the question is, what do we mean by quality? So these are some of the evaluation metrics, which is data erasure completeness. Has the influence been removed? Unlearning time efficiency. Is the unlearning efficient for all feasible forget sets? And membership inference attack. So I'll be looking into membership inference attack. So that is a model that attacks the unlearning algorithm, and it tries to distinguish based on the model parameters if an image is from the forget set or test set. So what we are trying to do here is that suppose the data has been forgotten well, right? So you would expect that a forget set data point looks as good as, almost similar in distribution to a test set point. Does that make sense? So to the model, a forget set point should look similar to a test point, because this data has been forgotten. Does that make sense?
You're saying to a model, forget set.
Yeah, so to a model which has effectively forgotten the forget set, means now this model is as good as not been trained on the forget set. So the forget set point should look similar to the test set point, to a test set point, because it has not been trained on this.
So that is what is being measured by this membership.
Yes, so this membership inference attack will try to distinguish using this model whether that point was from forget set or from the test set. Okay, so that is the membership inference attack. So for the dataset here, we'll use the CFAR 10 dataset, which consists the 60,000 color images in 10 different classes. and there are different classes such as aeroplane, car, birds, automobiles, etc. And 10% like each class has equal number of images. So this is the CIFAR 10 image label data set. So 50,000 are the train points and 10,000 are the test points. Is that all right?
Yeah, carry.
Yeah. So results and inference. So this is the performance of fine tuning using MIA model for evaluation. So this is the pre-trained model. So as you can see in pre-trained model, the attack accuracy was about 0.58. So the MIA model was able to distinguish between test set and forget set with an accuracy of 0.5, which is not great because the accuracy should be near 0.5 if it can't distinguish, right? If you just use a random model, then you will get a test set or a forget set point with 0.5 accuracy. But since this is 0.58, you can see that this is not great. And so after unlearning by fine tuning, you get so this pre-trained model means the original model, A of D. So this has not been unlearned or nothing has been done, and we just map it on test set and forget set. So you can see the forget set losses are way less than the test set. So it is easily able to distinguish whether that point is from the test set or forget set using these losses. And after unlearning by fine tuning, you can see that the losses look very similar. So this model then can't distinguish whether this point is from the test set or the forget set. So the attack accuracy is near 0.5. Does that make sense?
I'm trying to understand. I'm not very clear. So you have performance of fine tuning using MIA model, and then retrained model attack accuracy is 0.58. Test set.
So the attack accuracy near 0.5 means that the model is not able to distinguish between both of them. And the further it is, the more it is towards one, it means that.
Wait. Attack accuracy. What is around 4.5?
The this attack accuracy here, the attack accuracy is 0.58 here.
Where is it 0.58? I can't see.
On the pre-trained model, below the pre-trained model, attack accuracy 0.58 is given. Wait, just a second.
So it's not able to forget. See. So attack accuracy around 0.5 mean model is not able to forget it easily. After unlearning by fine tuning, the attack accuracy is lower. Yeah. And what is this test set? Forget set. So performance on. So test set and forget sets are behaving okay. Unlearning by fine tuning. Hello. Yeah, the attack accuracy has reduced, if that's what you want to communicate, and the test and forget set performances are similar. That's another thing we wanted to achieve, right? Hello. Am I correct in these 2 points? After unlearning by fine tuning, the attack accuracy is reduced, and the test set and forget set performances become similar. Can anyone hear me?
I can hear you.
Sorry, hello, I was muted. Sorry. Am I audible? Shall I go ahead?
Yeah. So am I correct in those two statements? After
Yes. You are correct.
And the test and forget set performance also becomes similar, which is so
yes.
Both are two good indications.
Yes.
Okay.
Yes. Shall I go ahead?
Okay. So what you're doing in unlearning by fine tuning, again, I'm trying to understand. You're basically you just take the previously trained model
So we take the trained model and then we take some few more gradient descent steps on the retain set only.
Train model and few
Yes.
more GD steps on the
Retain set
retrain model.
only, not the forget set, only the retain set.
When it is a take the train model, you mean the pre-trained model,
Yes.
not the previous model. So you have to always preserve a pre-trained model, right? You can't do that. I mean, that's too much. I don't think you'll start with the pre-trained model, right? How many versions will you have? You'll start with the existing current trained model, no? That's what you mean. In
Yeah, sorry. By pre-trained model, I mean the current trained model here. So I will change that. The pre-trained model at all steps means the current trained model.
oh,
So while yeah, so we used ResNet for this. So by pre-trained model, we meant a trained model, as in we just wanted a model that has been trained to perform the classification. So that is why we use the pre-trained model, because we didn't have the resources to train the ResNet again. So
okay.
is that all right?
Yeah.
Okay, so now we this is the adversarial attack that we are going to perform here. So we'll choose a adversarial forget set where all the examples in the forget set are only from one class. So say in our example here in for CFAR 10, we chose all the examples of automobiles, and that will comprise our forget set. So we want to forget everything automobile. So that is the adversarial attack that we are performing here. So for example, this can be very useful in the sense that I want to forget all occurrences of someone's face and someone say named Ram or something. So we want to forget all Ram's faces. So all class labeled Ram examples should be in the forget set. So forget set comprises of all examples of one class only. Does that make sense?
So this is your formulation you're saying. So far, you only presented.
Yeah, so far was the general literature on this problem.
Go ahead.
Yeah, so this is our addition. So forget set is all automobile images. Test set is as usual, and we used fine tuning on the retain set. So in this case, what happens is that if we run it normally, then the attack accuracy increases to 0.95. So the reason for this is that we are performing the attack on the entire test set, and the forget set comprised only of one class images. So now after unlearning, it has forgotten how to predict class automobile. And it can predict all others well. But now the test set distribution comprises of all kinds of images.
So this is catastrophically forgetting, right? It has forgotten the original some classes.
Yes. No. So the thing that happened here is the forget set. Now it has forgotten how to classify things as 0, right? So for the forget set, the losses are high. But what happens is the test set comprises of all classes. So for the other classes, it still remembers how to classify them. So for non-automobiles, it can still classify.
The test set will still consist of automobiles, right?
Yeah. So that is what we changed ahead. So we now change the test set to consist only of automobiles. So I'll just yeah. So here then what we do to
only consist of automobiles. I'm not understanding. But
okay, I'll explain it a little clearly. So initially the test set is the entire test set, right? And now our forget set is comprised only of automobile images. So what we would have got if we would have just run the MIA algorithm as it was before, which was comparing the forget set and the test set points and training a model to distinguish between test set points and forget set points. If we would have just done that with the entire test set, then what happens is that the test set comprises of classes of all classes like aeroplanes, cars. So now the model does not know how to predict automobiles anymore after unlearning, but it can still very well predict the cars, planes, etc. So the test set losses are high for automobiles, but for the other classes, they are lesser. So this MIA model can very easily distinguish whether a point is from the
I'm
forget
not
set or test.
understanding. I'm not understanding. So choose an adversarial forget set. You forget automobile. How does it affect existing techniques?
So this the existing technique was to take the forget set, test set, and then train a model to distinguish whether a point is from the forget set or the test set. Does that make sense?
Okay.
Is that all right?
Existing technique, distinguish if a model is from forget set or test set.
If a point is, yes.
If a point is, yeah. Okay.
Does that
So what are
make
you
sense?
doing here? Yeah, then what are you doing here?
So here now the forget set is comprised only of one class. So what happened is that the model forgot to classify things as that class. So now the model will never classify something as automobile. Say if it has forgotten,
But that is
all the
purpose,
forget set.
So
What?
Is that a problem? Because you didn't want the model to classify as automobile. So what is the problem?
No, the problem is this attack accuracy is very high, so that would make it seem like the unlearning has not happened. So just going by this metric, you will say that the attack accuracy is high, so the model has not unlearned properly. But so that is incorrect.
So the problem is with the evaluation. No? I mean, how can we say the model learning?
Yes, the problem is with the evaluation.
Okay.
So this evaluation will incorrectly label this unlearning as not great, as not good. Is that fine?
Yeah. So you're going to change, next step is going to change the evaluation, is it?
Yes, we are going to change the evaluation so that the test set must distributionally match the forget set to ensure that we are evaluating it correctly. So this is what happens if you match the test set to the forget set. So now even the test set has only automobile examples.
But I thought you'll remove, no? The test set should match, it should not have automobiles, right?
We will do that also later, but this is to test the unlearning that has occurred. We should have only automobile test examples, right? Because test examples which are not automobile will be predicted very well by the model. So it will, the MIA membership inference attack will very easily be able to distinguish a automobile from a non-automobile because non-automobiles will have very less loss. So to effectively test if the unlearning has happened or not, we want to basically check if it can classify, it can give very less loss for an automobile, which should not happen. Does that make sense?
So the loss will be low.
No, loss should be high. If the test set is autumn.
No. If it is forgotten, then accuracy will be high, na? Because test set consists only of automobiles and the forget was also automobiles.
Yeah, so if it has forgotten automobiles, then it should give high loss or low accuracy for it should never predict automobile. Right?
Yeah, so that's why
if it has
you should never predict automobile. For the test set which doesn't have automobile, your accuracy should be high because you have forgotten automobile.
Yes, correct. Agreed. For a test set which does not comprise of automobiles, we should have high accuracy. That we'll get to that later. Should I go ahead then? Is this part fine? Okay.
So the test eval set has only automobiles and forget set also has automobiles and the accuracy will be high. We agree, right?
A test set, forget set only has automobiles, test set only has automobiles, then both should have high losses. The data points in both both sets should have high losses.
If forget set has only automobiles and test set has only automobiles, the ideal model should give 100% accuracy in test set, saying none of them is automobile. They're saying that I don't know, or you're saying it'll it's forgotten. So what will it do? You're saying it'll have low accuracy.
Basically, I'm saying that suppose a test set, the forget set is only automobiles. Now, if the unlearning has occurred properly, this model has never seen an automobile example, so it will never predict automobile for anything. Is that part fine?
Yeah, okay, fine.
So now if the test set gives automobile examples, it will still predict something else for that example because it has never seen an automobile example. So it is as good as, yes, never been trained to give automobile at all. So it will predict other things for automobile examples. Is that all right?
Right.
Yes. So that's the reason the accuracy will be very low for automobile examples, but the loss will be high. Is that all right?
Yeah. So how are you fixing it?
Yeah. So to fix it, no. So this part is saying that to check whether the unlearning has happened properly or not, the loss should be high. So this part is checking the loss for the forget set and test set, and they both should be high such that they both are not distinguishable. So given a point, you should not know whether it's from the forget set or the test set when both are all automobile.
So low accuracy and high loss with the test set containing instance of forget set means that
so both test set and forget set are automobile now. So the model should give high loss for both. The model should not predict automobile because it has been trained on data which is entirely not automobile. So given a point,
no, so low accuracy and high loss with test set consisting instances of forget set. Low accuracy and high loss with test set consisting instances of forget set means the model has forgotten.
Yes.
Okay.
Okay, so the unlearning is tested by this. But what happens here is that we tested the unlearning, but we didn't test the performance maintenance. That after unlearning, the model should retain its performance, right? So that reduced. So this is the test set accuracy before. This is the entire test set, except automobile. This is all test set comprised of everything apart from automobile. So accuracy on that should be maintained, right? So that decreased. So the reason for that is overfitting, because we what we did is we basically overfit the data on the retain set, right? By fine tuning, we trained for a few epochs just on the retain set.
Right.
So this problem lies in overfitting. So we added a new term to the loss where we penalize the model from straying too far from the original weights.
No, but accuracy should be low and loss should be high if it has actually forgotten. Na? So why are we trying to not make it not forget? So I'm very confused. We only agreed, both of us agreed that low accuracy and high loss with test set containing instances of forget set means the model has forgotten well. Now why do you suddenly saying that it is overfitting? You don't want the model to forget?
Because
I'm not
that test set was of the same class as the forget set. In this slide, this test set is of the same class as the forget set. So all the test set examples here are automobile. On the other hand, this test set is of everything except automobile. So this is not of forget set, like not of the class of the forget set. These are all the examples of comprised of labels which are not the forget set label. So on these examples, the model should maintain its accuracy, right? It should not forget to classify aeroplane just because we told it to forget automobile.
I think we are running out of time. Then we can move on.
Okay, I'm almost done now. Just 2 or 3 slides left.
Yeah, sure.
Is this?
So you're saying in contrast to earlier, the test set.
Yes, in contrast to earlier, this test set is comprised of only of automobiles.
It does not contain automobiles.
And this test set, yes.
Instances of the forget set, and this means and therefore low accuracy means overfitting / underfitting is also possible. It's also underfitting possible.
I'm not entirely sure.
Yeah. Okay. Go ahead.
So I hypothesize that this is due to overfitting, and thus I added a term in the loss where you should not stray too far from the original weight. So you have a term which is just the current weights minus the original weights norm. So you don't and some hyperparameter in front of it. So we added this term to the loss where we penalized the model from staying too far from the original weights, and that led to an increase in the accuracy, test set accuracy, while still maintaining the fact that this unlearning attack accuracy is 0.5. Is that all right? So we added this term to the loss, and we saw an increase in the test set accuracy while maintaining the fact that it is capable of unlearning the data, forgetting the forget set.
I didn't understand. What are you proposing?
I am proposing an additional term to the loss where we penalize it to stray too far away from the original weights of the model. So we are given a trained model, right? Trained model has some weights. Now, when I'm fine tuning it, I don't want it to completely overfit on the retain set. So I'll give it some loss penalty to stray too far from the original weights. I don't want it to change the weights completely.
Your penalty if it strays. So penalty.
Yes,
that ensures
if it goes
that
too far from
the weights don't far. In which setting? In which setting?
In which setting, as in?
To avoid this overfitting, you're saying?
Yes, yes.
Okay, go ahead.
So with that, we see an increase in the test set accuracy while the model maintains the fact that it has forgotten the forget set. So it has still forgotten the forget set, and the attack accuracy is 0.5. That means that the membership inference attack is not able to say whether the point was from the test set or forget set. That means that this attack accuracy is maintained while the test set accuracy increase. And note that this attack is on a test set which is same as the forget set, while this accuracy is on a test set that is all except the forget set class. Does that make sense?
Yeah. Okay. Yes.
So that is all. So these are some of the references.
Okay. Interesting. So I think what about code? Can you just quickly give a glimpse of the code?
Okay, I'll open it. Just a second. Yeah, so this is the code. So this is just importing stuff. We have used the NeurIPS 2022 Kaggle competition code and then built on that. Hello, am I audible?
Okay.
Yeah.
Okay, good.
So we have used the NeurIPS 2022. There was a Kaggle competition for unlearning. We used that code. We have referenced it and we built on that. So this is the code. This is where we modify the test set to comprise. Here I'm comprising of everything except the automobile class, that is class 0. So this is the modifying the test set, and then this is the CIFAR data set. This is the unlearning algorithm that we wait.
So you have checked in all this, right? You have checked in all this, right?
Yes.
You have uploaded all this, right?
Yes.
Okay. So Vishak, do talk to them if you think there will be some interest from your existing work perspective. I mean,
Yeah,
it
sure.
can be taken. Basically, if it can be taken to a publication, I think you guys are interested in making that happen.
Yeah.
Okay.
Okay.
You're in a third year.
No, actually, I'm in the 4th year. So I currently have a placement.
Okay, and both of you.
Yeah.
Okay, but Vishak, just talk to them. See if you can share your contact with each other.
Yeah,
Thanks.
sure.
Yeah. Thank you. I'll exit the meet then.
Thanks. Yeah, the next team.
Now then you can start presenting.
Yes, Nandan. Can you please start?
Yes. Sharing the screen.
Yeah.
Okay, so the research paper we presented in the seminar was auditing large language models via discrete optimization, and we have implemented a part of that paper in this project while trying some
I want to ask one
methods which
question upfront. Is this contribution fair in the sense everyone has equally contributed?
Yeah,
Yeah.
like everyone has equally contributed.
Okay, and likewise for seminar, I'm assuming. Okay, thanks. Go ahead.
Yeah. We basically sat together and ideated and implemented things.
Okay, sure. Go ahead.
Okay, so in that paper, we had discussed joint optimization for the prompt and output pairs for toxicity. That's what we have done here primarily.
So basically, what we were trying to do is for any what the paper talks about basically is for any normal non-toxic input, can we find a way to find if the LLM gives out toxic outputs for non-toxic inputs. So the notation here is the same as previous. X is the prompt and O is the output. And the paper, I mean, this is very summarized version of the paper, and just the important things that are needed as a recap. Nandan, can you go up on the first page only? Yeah. So SI, if you look at equation 1, SI is a score that we define, and SI gives out the probability that the output is toxic and the output is generated by the LLM. So they use the log probability, that they try to maximize log probability that for a given input prompt X, we get a toxic output O. So the toxicity part is handled by the phi that you see on the left side, and lambda times log probability of LLM is trying to convey the fact that the output is indeed greedily generated by the LLM. So this SI gives out a score, and we try to maximize this. We try to maximize that the output is toxic as well as it is generated by the LLM. That is all that's here. Now this SI, we try to split this SI into
So maximize the probability that output is toxic.
Yeah, right. Because when I say greedy, hang on, I kind of get your question. So they try to maximize SI, a score that is high when the output is toxic. So they try to maximize the score and try to see whether like which are the prompts that will give out a toxic output.
So maximize score SI that the output is toxic.
Right. No, SI is a joint score, technically. Joint score that given that prompt, LLM generates an output. So this lambda times log probability is making sure that the output is that particular output for a given prompt. And phi is the toxicity parameter. Phi kind of only depends on like whatever the output is for a given X. Is that fine or? So here's the thing. So SI, think of SI as a score. There are two terms in SI. One of the terms make sure that that the output that we get from an LLM greedily is the same for whatever input we give, we get an output from an LLM, right? So SI is a score that makes sure that the output is toxic.
Independent of
non-toxic agent.
even for a non-toxic agent.
Yeah.
Okay.
So
But
the reason why they use this
minimax problem.
Yeah,
want to
right.
learn
Nana, if you
parameters
can you I think I have a better it's better represented in the paper. Nandan, can you just open the paper, the original paper for like 1 second?
as your
Can you move down to where they have written the equation? थोड़ा नीचे. This thing. This map in like above.
Can you enlarge it a bit, please?
Yeah. Further up. Further up. No, not this one. Further up. Yeah, this one. So if you look at equation 2, we're trying to maximize.
Just enlarge, no? Just enlarge, no?
Yeah. Can you zoom in on equation 2?
I'm just kill the all. There's a cross there. There's a cross there. Bookmarks and all tools.
Yeah, turn off the bookmarks and all tools.
Hello. Okay.
Yeah,
So,
equation 2, by the way, not 3. Equation 2 is more intuitive. Yeah, so phi x comma o is a function that gives out whether for a given prompt x the output is toxic or not. Because phi, we'll talk about phi separately, such that f of x equals to f is our LLM, x is our prompt.
So their phi is the same as your SI, right?
No, SI is a combination of phi and this constraint. So this constraint is non-differentiable. They convert the constraint into a differentiable constraint, and then so that's why they take the log probabilities of it, because this f of x equals to o happens greedily. Every next token is picked up greedily, which is just argmax, and it's not differentiable. So to convert that into a differentiable function, they use log probability and they multiply with a parameter called lambda. So if you look at equation 2 and 3, they are basically the same thing, but just this maximization of log probabilities instead of a very hard constraint like equality. In equation 2, it's an equality constraint that the LLM should give out this output only. In 3, we try to maximize the probability that it is actually giving out that output. Does that
but there's no min-max problem. You're just maximizing.
Yeah, that's not there is no min-max thing, only maximization. They do a coordinated ascent to maximize this whole thing.
For a non-toxic output.
Yeah, we get it out toxic output. So they're not trying to like fine tune the LLM. They're just trying to find whether a given LLM gives out toxic outputs or not. So they're not trying to correct.
Okay,
they're not
auditing.
trying to find.
It's not training.
Yeah, it's auditing. Right.
Okay.
Yeah, Nandan, can you go back to the report? Nandan will go back to the So now SI is something that we're trying to maximize, because SI for whatever X and O, SI will be if SI is maximum for some X and O, we can say with surety that for a given prompt X, that O is the output by the LLM and that O is toxic. That is what SI sort of shows us. So we're trying to find those pairs. We're trying to find those prompt and output pairs. जिसके लिए this SI thing is maximum. Now this approximation, they split it into basically two terms. One is a linear term and another one is autoregressive. So yeah, this is something that we talked about in during the paper presentation. This approximation happens and they have given proofs for it. And basically they try to split it into linear and autoregressive at a point where in the out. So let's suppose if we modify one of the tokens. So for an LLM, every token that comes, it's an auto-regressive thing, right? So every token that comes after that modified token depends on that token that we changed. So this is where they split it into auto-regressive and linear term, and they have a linear approximation which boils down to this equation 3 that we see over here, uh, which is just the dot product of embeddings with the gradient. Yeah, so then can you move down, further down? Okay, so a few experiments that we tried, I think 3 or 4 experiments. A couple of them worked, a couple of them did not work.
So what was the
Yeah.
motivation? You were just trying to replicate their numbers, or
No, we were able to replicate their numbers. We were trying to motivation was to, in fact, like, can we make it a little faster? Can we make it so since their objective is to find those examples, find those toxic outputs, right? So we were trying to see, can we make this thing faster, because currently it's very slow. It takes a lot of time to run. So what we were trying to do is, can we make it more can we find new examples? Can we make it a little faster than it already is? And can we, make it more accurate? So uh, they have a linear approximation. To make it more accurate, we thought of trying a second order approximation that involves this Hessian term that is there. But this is an experiment out of the 3 or 4 experiments that we did that did not sort of worked out, because it required a lot of time calculating the Hessian and stuff. So yeah, but we've mentioned it here for completeness. And then we again tried a BFGS kind of update, but similar thing, like it requires a lot of RAM. Plus the BFGS term is only like it's only accurate near the optimal value. So approximating a Hessian within our algorithm using BFGS would not have made sense, because we need the Hessian at each point for the SI approximation, for the approximating that score. And BFGS in itself is an iterative algorithm, so it requires some iterations to actually converge to the Hessian matrix. So that is why this we had to like drop this idea as well. One thing that did yeah, Sumit, I think you want to say something.
Nothing. I was just saying, like, the above basically two experiments was in view of increasing the accuracy. In the basically we thought like including the
can others mute themselves? It's too much echo.
Hello. Hello, am I audible?
Yes, you are. Go ahead.
Yeah. So basically, the paper were using a first order approximation for the basically approximating the next iterate of the like optimizing objective. So we thought of including the Hessian to achieve a greater accuracy, but basically it turned out to be computationally very expensive, and most of the time the GPU RAM was getting crashed. So we weren't able to implement that. So we actually have eventually we have to ditch that thing. So we again thought of yeah, Vinay, you want to say?
Another, can you like move further down? I think
Fine. So I think your BFGS impractical or not serving the purpose of
right.
making the inference faster.
Right, because if you look at the SI term, there is a dot product between the embedding matrix and the gradient of the embedding matrix with respect to the objective that we defined. So the embeddings themselves are huge, like there are 50,000 words in the dictionary. So it's just huge. I mean, storing it in RAM and taking dot product would require like some sort of engineering to get through this. Instead of storing all the gradients and all the embeddings and then taking dot product, which is like storing tensors of 50,000 cross something, So I think we need to engineer our way out of it to actually perform it. But we have other experiments that we like more. We spend more time on doing them. So yeah, Nandan, can you scroll further down to the modified ARCA algorithm? Yeah, okay. So yeah, no, not this one, the algorithm 2.
Yeah, this is algorithm.
Right, okay. I think your screen is lagging or something. Should I share my screen?
Oh, let's proceed.
Okay. Okay, sure.
You may want to go a little bit down, scroll a bit more down, and then
yeah. I think Nandan, your screen is frozen. Can you stop sharing? I'll share my screen. Okay. Is everyone able to see everything?
Yeah.
Okay. So this is the modified algorithm. We made a small change to their algorithm. The way this works is we sample out some random zoom in over here. So forget, I'll explain all the other functions that are required. We sample out some random tokens that will be our prompt. Now with we sample out an epsilon from a normal distribution, and if that epsilon happens to be greater than 0.5, we randomly sample from the same dictionary. Otherwise, we have a subset. A subset is basically a subset of this V. We're calling it subset variable. It's a subset of this V, which actually contains toxic output. So ultimate goal is to find those prompts for which we get a toxic output. So instead of randomly sampling from the whole in their ARC algorithm, so this is their paper, and what these guys do is they randomly sample outputs as well as inputs from the same dictionary. Now, to make this a little fast, we instead of sampling outputs from the dictionary itself, we in some epochs we sample it from a subset. This subset is toxic tokens subset. How we created, there is another algorithm in algorithm 1. I'll go over it. But this subset for now contains toxic tokens, some abusive words or not just abusive word, it also contains French words. For example, if the input prompt is in English and the output is coming out to be in French, that is also not something that is desired, right? So instead of sampling randomly from the vocabulary, we sample from the subset, and we have this sort of exploitation kind of thing happening that usually happens in reinforcement learning, where we sample out an epsilon. If it is greater than something, then explore, otherwise exploit, something like that is what we tried. Now for the rest of the algorithm, it is the same. We calculate. Now we have a candidate X, we have a candidate prompt, which is some tokens, we have a candidate output tokens. Now we run the whole ARC algorithm as it is, as they have mentioned. We find out, we basically calculate this fee, and
so
we
basically,
yeah.
You're just pruning the set of entities with which product would be completed, right? You had to EV transpose EJ that you showed over here. And now you're trying to ensure that the dot product computation is model of J.
So we're trying to reduce. Yeah.
Each dot product computation will still take the same time.
Right, it will still take the same time, because that needs to happen for the candidates. We're trying to reduce the candidates that are there.
You're trying to reduce the number of dot products.
Right.
Yeah.
So rest of the algorithm remains the same. We calculate the SI score as defined theoretically. Here this happens in this get candidates function, which returns
So
some
there's a
top
lot of work,
case.
by the way, I can point you to it. There's a lot of work on how you can effectively using try. You heard of try?
Yeah.
So prefix trees, etc. You can use them to efficient. Efficiency is the concern. There's a lot more you can do to even get to the subset.
Right. Yeah.
So what you have done is like by fiat, discarded several entries. But you could also stick to the existing entries, but index them.
Right, but I don't think there is any way of knowing whether they're toxic or not. I mean, I think that requires some like finding out whether the token is toxic or not. So that is something for which we need some sort of other language model at work.
But you actually determined the toxic entries, no? How did you subset?
Yeah, so that is in another algorithm over here in which we use some open source models that were present on Hugging Face. This was a one-time thing because we create that subset once and then we use it. So we used open source models to iterating over every token in the dictionary. For once, we classify them whether they are toxic or if they are not English, like not English or they're of some different language or stuff. So that's how we created the subset basically. Yeah. Yeah, and then we find some top K scores and we take the argmax from the top K of SI values. So I think Sumit can talk about the results that we get.
Yeah, go ahead.
So basically in the paper, Abhinav, can you
not speaking. Please mute.
Yeah. So basically in the paper, they implemented the joint error optimization part, keeping the prompt and output pairs nearly of the same number of tokens. Like they have one case in which they had the same length of the token and the prompt and the output, and in the other two cases plus minus one tokens. So basically, we the algorithm was performing well in shorter cases like 2 and 3, 3 and 3 and cases. We tried the algorithm basically to see how it performs in larger cases, longer outputs and variable of prompt. So we kept the prompt output pairs as a 10 plus minus 5 second. So we run the algorithm in these settings and we achieved it. We saw that in longer outputs, and when we want to achieve a longer output, which is short set, a longer prompt was giving a actually nice success rate, which was even better than the phases that the paper that have been implemented in the paper. It was like most of the time it was hardly one or two phases when it has failed, but in shorter prompt lengths, like 3 and 4, it was the success rate was too slow, but like too low. So basically, a success rate is defined as the number of output prompt and output pairs that the algorithm is not. Sometimes the algorithm gives a none from a none pair. So the success rate defined as the total number of outputs and none divided by 2. So and longer length. So that's the basically what we have shown of different prompt lengths in their success rates that we achieve. Yeah, that's Abhinav. You can go ahead with sampling all of.
So in the first experiment, all you have done is verified their own algorithm. There's no speed. There's 5 token prompt length. So and we get a higher success rate. Arca is their approach. Higher success rate, high increasing prompt.
Basically, we tune some hyperparameters too, like in the longer prompt set, longer output settings, the major of the tokens, like the sentences contains vivid precise repetition of words and some illogical words with illogical meaning of the sentences. So we try to increase the log complexity coefficient. The actual in the paper to compute our results, they have used I think 0.5. We set it to different values and achieve the results in 0.8 and a 10 plus 5 prompt output pair. So basically, these results in different hyperparameters settings. The results. Yeah, so that was this experiment.
Actually, your voice is breaking so badly. I couldn't understand what you're saying. So again, let me repeat. You're saying longer prompt output pairs. We include that when it's repeated use of same word. Actually, your voice is so poor. I mean, I'm only able to see the screen. I can't understand what you're speaking at all. So I'm just trying to read whatever I heard.
Now.
Yeah, what were you talking about? Long prompt output pairs? When this is just validation of their algorithm, right? There's nothing to do with your intervention.
Yeah. In this particular experiment, we didn't intervene with the algorithm part. We just tried to play with the hyperparameters and different settings of prompts and output, and verified the results, like what is the output of the algorithm. In this part, we didn't play with any.
Did you use their implementation or did you re-implement? Did you use their implementation or did you re-implement?
We basically we took inspiration from their implementation and we modified some parts of the algorithm. Like in the previous all experiments, we modified a major chunk of the algorithm, but in this one we did hardly many changes. We just took their algorithm with some slight changes, which we thought would be useful. Yeah. So.
Okay. So, I mean, I'm still not understanding what is so significant about prompt length. I mean, input prompt length. Our goal was something so different. I'm totally lost with your experiment. I'm totally lost. I thought the whole goal was being able to, audit, right? Now, auditing had to do with, you have a non-toxic input, and suddenly you're saying in long prompt output pairs. Not understanding anything you're saying there.
Basically, in the experiments that have been stated in the paper are limited to a prompt length of size 3 and an output length of size 2. And the paper claimed that in this setting, the algorithm performs the best. So we tried to play with other hyperparameters and tried to achieve a significant or even better results in different settings, like a longer set. Like in the paper, they have said in 3 token setting, the model wasn't able to perform really well. So that is what we were experimenting upon. So like the major algorithmic changes and experiments was in the part of that sampling one only, and then Hessian implementation. This was just take up with hyperparameters.
So the way they defined this average success rate is how many toxic pairs are we actually getting while the algorithm is running. So if we increase the prompt length, that is more number of prompt tokens that we have to iterate over. So it takes like even longer, and that improves. So average success rate is number of hits divided by total number of some outputs that we are getting. So as we increase the number of increase the prompt length, the total number of outputs, they sort of like increase. So to increase the average success rate, we kind of played with hyperparameters. But yeah, I mean, that is the least significant part of it. Yeah.
As the prompt length increases,
so the LLMs, they start to like give out lesser toxic output, because if it's a well-defined prompt, why would it give out weird outputs, right? So intuitively that way.
but the prompt is non-toxic.
Prompt is non-toxic, yes. And if it's longer, then toxic, the probability of getting a toxic output reduces, is what the paper says. But on modifying a few parameters a little bit more, we were able to find those examples where even for a longer prompt, we have a toxic output. So that is what it is in total.
Toxic fight. What is the x-axis success rate?
Exactly, success rate is. So when the algorithm runs,
but you have something called toxic 5 token at the top. What does that mean?
5 token is the length of output tokens.
So what is the x-axis here? Prompt length. What is the y-axis? What is the y-axis success rate? And what is this toxic 5 token sitting at the top?
We fix the number of output tokens to 5, and we sort of increase like the 2, 3, 4, 5, 6 prompt length is 5 tokens, 6 tokens, 7 tokens, like that. And success rate is the number of
but prompt length was varying, right? I'm very confused. Toxic 5 token and you say prompt length.
These are different experiments for every prompt length. Like once when the algorithm runs, prompt length is fixed and a number of output tokens is also fixed. So these dots are different experiments that we tried. Then we plotted.
So toxic 5 token output.
Yeah, output for 5 token output and 5 token input, 6 token input, 7 token input, like that.
So here also the input remains toxic free.
Toxic free, yeah. Randomly sampled.
And the original paper only talked about 5 token length, is it?
Yeah, they sort of fix token lengths.
But
there is no mention of. So there is very limited mention of changing output token lengths, and they don't talk a lot about changing lengths of, like, how does changing prompt length or how does changing output token length affect the behavior of the algorithm. They don't like. They haven't talked about.
You said you got results contributing to the paper, whereas the success rate is only increasing with prompt length. Or were they saying that success rate is independent of prompt length?
I think Sumit talked about the usual trend. So they have these.
See, possibly when the output token length keeps increasing, then the success rate may not increase with prompt length.
Can you repeat that?
I think the success rate is increasing with prompt length because the output is a fixed length.
Right.
I mean, what might matter is output by input ratio. The success rate might remain constant for a fixed output by input ratio, right?
Right. I mean, yes. That should have been an experiment that we should have tried, like varying the variation of number of output tokens and the number of input tokens together.
Yeah. So this plot is not surprising.
No, but this is following the usual trend.
But all you're saying is the original paper never reported this.
They don't experiment with longer output tokens. They do experiment with longer prompts, but not with longer output tokens.
Okay.
So for a longer token, output token, to be toxic, that's like lesser probable, right? Because then you have this whole.
Got it. Now coming to the other thing. As the non-toxic increases, the LLMs give out less toxic output. But then figure 2. Average prompt is 1 token logarithm. So where is output length? Here?
Okay, this output length was, I think it was fixed. Sumit, do you remember the output length for this experiment?
Yeah. In this setting, the prompt was 3 and output 2.
Oh.
No, but longer. Acha, x-axis is not length of the prompt, is it?
X-axis, it is
Yeah, the
prompt.
x-axis is prompt length.
So we start
So
with
then
2 and then we go on to 6.
Yeah, so
For
that's
each
what. So output length is
always fixed.
prompt
in all our
minus.
experiments.
No, it is not.
No, it is not.
Here, output length is always prompt minus 1. Prompt length minus 1. Right? That's what you're saying. When prompt is 1 to occur,
In these experiments, yes. In these experiments.
So your finding is that it kind of okay.
So this is when we explore from the subset, from the toxic subset.
This is using subset, is it?
Yeah. And the above one is from the paper itself.
Archives for the paper. Auto prompt is yours. Auto prompt is yours.
The second one, no, the second one is ours. The second figure is ours. The first one is from their paper.
So your observations are similar to the paper, right?
Right, slightly better than them. If you look at for 3 prompt lengths, they achieve around 0.8 success rate. We get a little better than that because we are sampling from the subset. Ideally, we should have plotted this on this to get a better approximation.
I see. Using the scale is low.
Yeah.
0.6. Sorry. What is auto prompt?
Auto prompt is another baseline that they compare their algorithms to. So auto prompt, Arca, and I think there is another one. There are 3 basically state-of-the-art ways of auditing LLMs. Auto prompt is one of them, which uses something very similar to their algorithm, but with a minor changes, some changes. That's a different paper altogether.
Okay. So I was earlier saying that success rate might remain for a fixed output by input ratio. But your figure 2 basically says instead of looking at ratio, look at the difference of the length. Right? I was talking about input ratio. You are saying output minus input. Or sorry, input minus output. So it's constant. It's becoming constant with input minus output. That's what figure 2 shows.
Right. But that's what figure 2 shows. But in figure 3, it's a different thing altogether because we have that subset thing going on in figure 3.
So what about speed?
Speed, that is what we were trying. For speed, I think, it won't be so initial thought was to make it more accurate using Hessians, but Hessians is added complexity. To make it faster, I think they are already doing a first order linear approximation. I think from there to make it even faster, that we were out of ideas.
Yeah. Purpose was to make it faster, right?
Yeah. So this to make it faster in a way that we get more hits, because the speed actually depends on the number of matrix multiplications that's going on, right? So that remains in a way that remains kind of constant, but we get more number of successful toxic pairs, non-toxic input and toxic output pairs for the same number of iterations that we run. So let's say if we run it for 100 iterations, we get 60 pairs compared to their 40 pairs. So that.
So you're able to do better exploration.
Right.
Okay. Vishak, maybe talk to them separately. But are you guys interested in taking this to publishable level?
Yeah, sure. I'm graduating. I think Sumit and
all of you are graduating.
No,
No, right?
only I'm graduating.
No, no.
Nandan and Sumit are not graduating. They're in third year.
Okay, then it's good. So maybe you can Ishaq note, right?
Yeah, sure.
Thanks, and I think please get in touch with Ishaq.
Yeah.
Likewise, get in touch with them.
Sure.
Yeah.
Thanks.
Yeah. Thank you.
Thanks.
Yeah, next.
Yeah, you guys can.
Hello.
Yeah, I'll just be back. You can start screen sharing. I'll just be back.
All right.
Please start the screen share.
Yeah. One second.
Kushal, can you
Yeah.
share the screen?
Yeah, actually, I have some permission issues. I will fix it. Like
Yeah, try
1 minute.
rejoining.
Sorry. Yeah.
Yeah, can you get started?
Yeah. So is my screen visible?
Yeah.
All right. So. Okay. So.
Okay, so
Hello, good evening. My name is Kushal Pavaskar and my teammate is Asif Sheikh. So our project was, we chose the project Bandit View on noisy optimization. So here is the problem statement. So the idea is to optimize an unknown continuous function on a continuous bounded set. And what we can do is what we are allowed to do is we are allowed to make a finite number of evaluations or queries to know the approximate function value in some range of domain, in some subdomain. So like basically if we have some arbitrary function and we are given domain, let's say 0 to 1, then we can choose choose the values of x, like let's say the domain is x, so we could choose x as the range, let's say 0 to half, and we could get, in return we would get a value about the approximate value of the function in that range. So it would be probably the mean value of the function in that range plus some error. So that error contributes to the noise, and based on all those noisy values we are supposed to optimize the function, or that is we are supposed to find the maximum value of the function. So Asif, can you take over
okay,
from here?
so let me explain the bandit view. Okay, so this is optimizing a noisy black box sort of function is a common scenario that we face, and the bandit view here comes in when we look at this as an online learning problem. So so the bandit problem is you have multiple options available. You can at each time step you can choose one of the options from which you will get a reward, and there are multiple like learning scenarios. One of the scenarios could be
in a finite number of time steps, you have to find the best possible option or best arm to pull. One scenario could be in a given number of time steps, you have to maximize the expected reward you will get from the on running the algorithm. So here you have a dual problem of figuring out the best possible option and also uh, exploiting that option to gain the maximum award that is possible. And another extension of this scenario is could be where the time horizon isn't bounded. So you don't know when the algorithm could suddenly terminate, and in this scenario you have to maximize the cumulative expected reward that the algorithm is making. Um, so that's the bandit view of the optimization problem.
Okay, so
Kushal,
yeah. Okay, so what we are using over here is the online optimization framework. So like Asif said, we get some return value when we make an evaluation. So in this online optimization framework, what the result of our evaluation is associated to some reward value. And so the objective over here is maximizing the sum of obtained rewards. So like basically we take the cumulative reward and we are supposed to maximize it at every time step. So when we do this, we have a trade-off between something called exploitation and exploration. So what these terms mean will be clear now. So exploration. So let's say we have multiple options available with us, right? So like when we are trying to optimize this function on a continuous set, we could choose different subsets to make an evaluation. So like those different kind of subset, those different subsets that we can choose are our different options. So what exploration means is we will try out all the different options and try to obtain whatever information we can. And then exploitation means exploiting a particular option which gives us good rewards by evaluating it multiple times. So we found out let's say the task would be finding out the best option. So when we find out the best option, we will just keep on evaluating on that option or querying that subset so that we keep on getting the best reward and thus the best cumulative reward. So here's one example. So our main objective is optimizing a function on a continuous set, but to understand a few things that would come later, it would be better to look at a discrete case first. So in the discrete case, like it's the online optimization framework only. So here we are considering a discrete case where the set of options is a discrete set. So what we have to do is we have to maximize the expected cumulative regret. So regret is basically the best reward minus the
we have
expected.
to
Sorry.
yeah, right. We have to minimize the regret, right?
Yeah, sorry. We have to minimize the regret or like uh, equivalently maximize choose the best rewards. So like we have to minimize the regret. So your regret means the max reward minus whatever expected reward we get from the option that we choose at a particular time step. So let's say that we are making an evaluation. So there have been n time steps and we choose some option at every time step. So we would get n rewards and thus n regrets. So let's say that based on these n evaluations, we find out some option which gives us the best reward. So that option would be option would have the expected reward given by max of mu I, where we are assuming that there are k options available. So and let's say that at a particular time step t, we are choosing some option given by it. Okay, so the expected reward from that would be this expected mu it. So since we are talking about cumulative regret, we are doing this n times. So this is a constant, so it will be n max mu I minus the sum of the expected rewards at each time step. Okay, now we come to something called upper confidence bound. So like how do we choose which option to evaluate at a particular time step? So like if we had some prior information that this like the one particular option has a greater chance, might have a greater reward than some other particular option, then we would choose that option which is likely to give us better reward. So for choosing that option, we look at this upper confidence bound. So it's given by BIST. So I basically means the ith option. S means so T is the time step, the current time step. So that means we have made T evaluations till now. Yeah, so we have made T minus 1 evaluations till now, and we are making the Tth evaluation. And S means the number of times that we chose the option I for evaluating. So then X hat I comma S is basically the reward of ith option, reward given by ith option in the S time step, S evaluation of that option. And this other term is
You
contains
said S is the number of times I was chosen.
Yeah, number
right?
of times I was chosen, and T is the total number of evaluations we have made. Like the T is the current time step. Okay, S less than T. Fine.
Yeah, and then what are you saying?
Yeah. So okay, so alpha is something called as exploration parameter. So why is
What is
that
the
term?
reward here? What is the reward
Yeah,
here?
reward is X hat I comma S. So in the Sth evaluation, the reward obtained is X hat I comma S for the option I. Okay, so now
what is the
here,
second term doing this? Square root alpha log
second
T.
term, second term contains something called alpha, which is called the exploration parameter. It's a positive value, and it has this other term log of T upon S. So this is a very important term. So here if we see log of T, so as time increases, it would increase in a log fashion. But when we look at S, it would increase in a linear fashion. So what happens is, let's say that initially we had some prior information that was some particular option, let's say option 1 had the best upper confidence bound. So we would keep on choosing that upper confidence bound, and we would keep on getting some reward. So if something does not happen and it's the distribution of the upper confidence bounds of the different option does not change, then we would just keep on choosing that same option. Whereas it might happen that by choosing some other option, we might end up getting some better reward in the end. So what this term does is, so here S would increase linearly in that case when we keep on choosing the same option I, and log T would increase in a log manner. So this would actually increase in a sublinear way. So what happens when we are choosing, when we continue choosing option I, but what happens when we look at the options that we haven't chosen? So in those cases, S would not change, but log T would keep on increasing. So what happens is, for the options that we keep on choosing, the BI, the upper confidence bound, keeps on decreasing if we ignore the reward for now. And the options that we aren't choosing, for them, the upper confidence bound keeps on increasing. So this allows us to
So the
kind of,
the upper confidence bound, again let me repeat.
Yeah.
Keeps increasing for those options which we have not seen so far.
Yeah, which we do not choose, right?
Because it has a 1 upon S, right?
Yeah,
the
right,
less
1 upon S. Yeah,
the less
S
you
would be
choose.
lesser, so log T would keep on increasing, but S would not change, so B would increase for those options. So there would come a time,
As time increases also, it would bound would increase.
Yeah, as time increases, bound would increase. So yeah, so there would come a time when the upper confidence bound of the option that we keep on choosing would become lesser than those of the options we do not choose. So in that case, we would start choosing the other options, those that have greater
irrespective of the reward.
So this is something called the exploration phase. So like this, so we don't actually know what reward, this is a like a random kind of a random number, right? So this is just a bound, but it might happen that actual reward that we get from some other query, from some other option might actually give us better reward. So like we need to actually explore and look at that. So this is what helps in choosing different options. So that's why this alpha parameter is called exploration parameter. So if we give a larger value to alpha, we would be like shifting between options more frequently, and for lower values of alpha, that shift between options would be less frequent. And then coming to the
Wait.
Yeah.
Can you go back? For large
Like,
values of alpha, sorry, can you repeat again?
yeah, so
Alpha
if
is
we
the
have
exploration parameter. So more
exploration
the exploration.
parameter, yeah,
The
so
more the
more the
more you
exploration parameter, more this increase,
the more the more.
more would it increase, more would log t by s increase for the other options. So in that case, the shifting between options would be more frequent. So we would be exploring more.
And Rn is the same as X.
Yeah, Rn is the regret. So mu I x hat is the same as mu I, expected mu I.
Yeah, sorry.
Right. Yeah.
Xi. Yeah.
Yeah.
Why have you used different notations? Xi is the same as mu I. Right?
Yeah. So in the book it was like that.
So xi hat actually is the mean of mu I. Yeah. That's why the notation is different.
Yeah.
You can move on.
Rn is the
Is that fine? Can I move to the next slide?
Yeah, so the Rn is the
Okay. Regret, cumulative regret. So best reward minus the current reward, sum of those. That's a regret.
Right.
Yeah, okay. Can I go to the next slide?
Yeah.
Okay. So let's just keep this discrete upper confidence bound, what we learned over here in mind. Let's keep that aside for now. Now let's come to the continuous case. So that's our main objective. So here the f is the function that we are supposed to optimize, and we will just call it something like a mean payoff function, like something that gives us reward. Okay, and it's defined on the set x, where x is a bounded continuous set as we defined earlier, and also f is also a continuous function. So now we choose now we make some sequence of subsets of x, so given by p h comma I. So here we are giving it notation like h comma I because we are going to represent it as a binary tree, where h stands for the level of the node, and I would be the node number at that particular level. So if you look at p of 0 comma 1, that would be the root node 0 comma 1, and it would denote the entire set x. Okay, so then its children would be 1 comma 1 and 1 comma 2, and so on. So we are considered, so h is greater than equal to 0, and I would grow from 1 to 2 raised to h.
Subsets of X.
Yeah, subsets of x, because we are going to be making evaluations at a particular subset of x. So
Okay,
so what's happening is,
can I take over
you
from
can
here?
take over. Yeah, you can take over.
Okay. So for the continuous case, the main conundrum is that in the discrete case, we have a finite number of options, and in the continuous case, we have an infinite number of options. So instead of thinking about the actual queries points that we are going to evaluate the function on, we think about partitions. We divide the domain into partitions and try to find the best sort of partition over which we can get a good reward. And the approach used in the algorithm that we have discussed in our project, the hierarchical optimization algorithm, is that we perform sort of a binary search kind of thing. So firstly, we need to understand what p h comma I here is. So p h comma I defines a partition. Um, So PH means that the domain, consider the domain to be from 0 to 1, has been divided into 2 raised to h parts, and I denotes that we are considering the ith partition of these 2 raised to h partitions of the domain.
What is H again? What is
According
H
to
again? What is H again?
H is like
H
dividing
is the
the domain into 2 raised to h
depth.
parts
Right, the
intervals.
node and the depth.
Yes.
Okay.
So if we have a partition h comma I, it can further be subdivided into partitions h plus 1 comma 2i minus 1 and h plus 1 comma 2i, and these are the two partitions that we'll obtain on dividing h comma I. So the motivation for further dividing partitions is to get a like corner the point at which the function is optimal um, to a higher degree of accuracy. Um, okay, so let's move on. Kushal, can you
Right.
go to the next slide?
Yeah, and
Okay.
also basically, if you look at the h comma I and h plus 1 2i minus 1 h plus 1 2i, so the subset chosen over the subset corresponding to these children are actually the subsets of this parent as well. Yeah, is that right? Right. Okay, let's move on.
Subsets belonging subsets.
Yeah, the children would also be like each node corresponds to a subset, right? So this is a
So
parent
the
and these are
children are
children. Yeah.
basically
Yeah.
so the children are basically disjoint subsets of the
Okay.
Yeah.
parent.
Go ahead.
Right.
Yeah.
Okay. So this is how the HO strategy is implemented. Initially, we create a tree and initialize it to just the root node, which is 0 comma 1. Here 0 comma 1 are the h comma I uh, from the notation we introduced in the previous slide, which denotes the entire interval from 0 comma 1. And here what we will be doing is we'll be evaluating upper bounds on similar to the UCB algorithm on the expected payoff on choosing a random point from this particular partition. So this is how the algorithm works. You initialize h comma I to 0 comma 1, which is the root node, and then you maintain the path that you are going to be following in capital P, and perform this while loop. So here in this what happens in this while loop is you traverse down the tree along the path of
Oh, P is the
along the
path.
path
P
of
is the path and not partitions.
Yeah,
no
this P,
yeah, there is
this is a different
abuse
P,
of
the
notation,
bit like yeah.
right?
So this is a bit cursive P and this is
Right.
normal P. Yeah, like sorry for the
Okay.
bad notation.
So at, right. So at each node, we look at both of its children and go along the children which has the higher capital B, which is the higher, which means we are going along the node which has the higher expected payoff. And simultaneously, we are also storing the path that we followed in capital G. And we will do this until the tree is exhausted.
Store the path in capital P.
Yeah.
Right. And at the end of this loop, what we'll get is at the end of this loop, what will happen is for the last h comma I, that is a leaf in this tree, will it won't have any children, but we'll see further that the b's for values of b for the children of a leaf node are defined to be infinity. So basically, yeah, here, right. So the value of uh, b for the children of a leaf node are defined to be infinity. So can you go back to the last slide? Right. So basically, what I mean to say is the h comma I returned by this while loop would be a node which is not currently present in the tree. We store this h comma I in this variable capital H comma capital I, and here we then sample a random x from the partition p h comma I and evaluate it, and we receive a reward capital Y. Then we include this node h comma I into the tree and make it extend the tree along this node.
I'm still trying to understand for the last.
Hmm.
So what you do, so you keep doing this, go along the node which is the higher expected payoff and store the path in P, which is fine.
Right.
B is the path,
Right.
B is the payoff. And then for the last h comma I, the leaf, what you do?
For the last h comma I, what will happen is the last h comma I that we'll encounter would be
Wouldn't be actually part of the tree.
Wouldn't actually be part of the tree. So at one point you'll reach a leaf node which doesn't have any children, but we just define the value of b's for the b for the children of these nodes as infinity. So basically what will happen is we'll choose randomly choose one of the two possible children, and we'll store it in h comma I, and uh, that would be the value of capital H comma capital I we'll get.
No,
So
saying,
basically we are trying
line number
to
11, line number 11. I'm
right.
talking about line number 11. You're
Yeah.
saying line number 11 is just
Yes.
breaking ties arbitrarily? Is that what you're saying? No.
Yes, yes.
Yeah.
It's
I see.
breaking ties arbitrarily. Then we choose a random x in this interval, and we correspondingly get a y. And the h comma I, the partition,
So
new
line
partition
15,
that we
line
had
15,
found,
what's it doing? Line 15, what is it doing?
it's storing the h comma I from the while loop in this new variable capital H comma capital I.
So when the while loop would end,
we could have right.
Yeah. Okay, so when the
Okay,
while loop would end,
that's okay. That's just bookkeeping.
yeah, okay, fine.
That's just bookkeeping.
Yeah,
Right.
that's just bookkeeping.
Bookkeeping.
And
Then
then
we extend.
Yeah, go ahead.
Right.
Asim.
So now we are extending the tree further along this node. So one thing we should keep in mind is when we are going further down the tree, we are sort of increasing the precision of the partitions. We are choosing to sample from narrower partitions. And then can you go to the next slide? Then there's the update step. So since since we'll be choosing one of the, finally we'll be sampling from one of the leaf nodes. We know that leaf node is a subset of all of its ancestors. So we perform the update step of the upper bound on the expected reward for all of the ancestors of this node that we sampled from. And this is what is happening here. That is why we had stored the path along which we had traversed down to the leaf node.
so you're saying you want to percolate it back.
Yes, we want to percolate it back.
Percolate what back? Sorry, percolate what back?
The update in the expected award if you randomly sample a point from this partition.
But what will it do at the leaf? I mean, I don't understand. Why do you have to go back to the root? You're fine with the leaf, right? What do you achieve by going back now all the way?
So in order to find the best leaf, we are going down a path, right? So
yeah, you found the
when
leaf.
we
Now, so you want to know its membership. You have kept its membership also. But why do you have to traverse back
right.
up? I didn't get that.
So
That's
we
because yeah, okay. So
what
that's
might
because
have
right, okay, fine.
What might have
What's the
happened is
purpose?
we might have right. We are keeping a track of the expected reward we'll get if we go along one of these partitions. So what happens is when you choose to sample from a leaf, this leaf is also a subset of all the ancestors of this leaf. So sampling from this leaf also gives us some information about the expected reward you could get if you would have sampled from one of its ancestors. So we should. It also sort of makes sense to
I
update
see, I see.
the
From
expected
expectation
reward for
perspective.
the ancestors.
Got it. From
Yes, from an
expectation
expectation
perspective.
perspective. Right.
Okay, got it.
And here the value. There are two variables here, u and b, and we'll understand the
Okay.
difference between them later. But
Yeah,
for
can you
now,
move?
let's just
Yeah, let's move forward. Yeah.
Right.
yeah,
Okay.
let's
So this is the modification that we have suggested. So uh, like here, what could like the in the original strategy, what could happen is that the depth of the tree could keep on increasing. Like there would like there is no we aren't really bound creating a bound on the max upper bound on the depth of the tree. So it could happen that like like one particular path that is taken might not result in like great like so yeah, let's see, let's so yeah, this v1 and new1 and row comes over here. So okay, so first when we look at first look at this term, the root to log n by thi. So like if you remember in the discrete case we had a similar term over here. So
Yeah.
so this term is also doing the same
Got
thing,
it.
like
Got it.
it's
Got it.
yeah,
Got it. Go ahead.
okay.
Go ahead.
And then there are these two other terms as well. So here rho is a value lying in 0 comma 1 and it's raised
So
to
this is
the
your
depth.
this is your modification you're suggesting
No,
to
no, I'm
PM.
yeah, I'm first explaining the reason behind why we are coming up with a modification.
We need to go a little faster here. Yeah.
Yeah, yeah, okay, it's almost done, right? So like here h is so rho belongs to 0 comma 1. So if we keep on increasing the depth, so this rho raised to h would keep on getting smaller. But the like it would get smaller in a submodular kind of way. So the extra information that we would get, that would actually be diminishing returns. So by following the same path, we aren't able to get a lot of information even by adding lot of like the difference
Sorry, I'm
between
getting an urgent
yeah,
call. I'm just
okay, all right.
गाइस कैब बुक कर लो अगर वो लाइक 10 मिनट में निकल सकते हैं.
हाँ या राइट, हाँ 10 मिनट बस हो गया, इसमें कुछ ज्यादा चेंज नहीं है.
yeah. Go ahead. Go ahead.
Right. So like what would happen is that as the depth keeps on increasing, we would actually get diminishing returns. Like we wouldn't get like much more as much information as we were getting by going deeper earlier. So what we suggest is that instead of continuing to follow the same path, we could like keep an upper bound on the depth that we have. We could define some max depth, and so that when that max depth is reached along the path, we could try and explore some other path. So what we are doing, so this the only change is happening that's happening is over here. So till here it's the same as the previous algorithm. So when we receive when we are comparing this capital H with the max depth. So if it's less than the max depth, we can add the node to the tree. But if it's greater than that, then we will just continue and try to go through a different path. So what would actually happen
No,
is that we would yeah,
are you saying this line number? What is the line number? 35.
35 line number 35. No, no. Uh,
The
here
difference is where in line number
line
35.
number 18.
Where is the difference? Line number 18 and line number 35 both. Is it?
Line number 18. So here, like after line number 18 over here, we are directly going through doing the update step for all HI belonging to P. But over here, we are doing this, like we are checking whether whether the depth would go beyond the max depth or not. If it does not go beyond the max depth, then we can add that node to the tree and then we can continue the update step. Otherwise, we would just start the loop again and maybe go through a different path. So this
If
actually
the
helps
depth,
us.
if the depth goes beyond beyond the
Yeah,
max depth,
right.
then restart.
Yeah, restart.
Backtrack all the way up
Yeah,
and restart, right?
yeah.
Okay.
So
That is the only
in that,
modification. That's the only
yeah, that's
modification.
the modification. So
Okay.
in this
Okay.
case, we would actually like probably save some time.
So what are
That would,
experimental
yeah.
results? Can we go to experimental results?
Okay, yeah. So, Asif?
Okay, so the experimental. Can you go back to the previous slide?
Yeah.
I'll just briefly go over what regret is. So, as defined earlier, regret is the difference between the maximum possible reward that is achievable and the actual reward that is accumulated by the algorithm. In general, our goal is to achieve sublinear regret. This is because if you constantly choose the same fixed random option, the regret you'll have this term would be constant, the maximum achievable award, and the expected award achieved by the algorithm would also increase linearly. So overall, we would get a linear regret. So the benchmark is we are
But that
doing
is,
good if
but that linear regret is what you would get otherwise also, right? It's not because of your modification.
no, I'm explaining why we would want to achieve sublinear regret, and achieving linear regret is trivial.
Yeah.
Uh, so,
Yes.
so the previous algorithm has achieved. Can you go to the next slide? So,
Can we go really
this is
close?
the
Yeah.
right. This is the plot for the regret that is achieved by our algorithm on one sample case where the we have a function defined on 0 to 1, which is maximum at 0.5, and it is sort of a piecewise linear function. And with that, I forgot to include the definition here. But anyways, as we can see from the plot, that the regret achieved by the algorithm is sublinear, since it's like downwards moving curve with the increasing number of iterations.
Yeah, but you need more experiments to verify this.
Yeah, right.
Yeah.
So also it's mathematically proven that the algorithm achieves sublinear regret.
You have proved it.
We don't have proof, so it was present in the reference that we were
No, but
using to implement the algorithm.
just by preempting, you have the only modification you have done is preempted the infinite increase of depth of the tree. By doing this, are you saying that you're getting sublinear regret?
No, so the sublinear regret was already present. So our modification sort of makes the algorithm more computationally efficient.
But I wanted to see that. Have you shown that it's computationally efficient? What are the benefits of doing that? You have experiments to do that, to show that.
No, we haven't included it in the slides.
So why no experiments in the report also?
Yeah, in report.
You have included the report?
No.
Hello?
No.
No, we have just explained our algorithm and the implementation.
But then your HO modified. You have no. You have finished the code. The code is done.
Yeah.
Yeah, we have coded it up.
You can run it also, right?
Right.
This is your.
Yes.
So
Yes.
the plot you showed is not using your code, is it? Your variant.
Yeah, it is using our variant.